Okay, I welcome all the participants to day 5 of our program. That is our online faculty development program on optimization technique, theory, practice, and emerging application. Today we have two sessions. The first session will be handled by Dr. Priyanka Chawla, madam. Madam will discuss about the particle sum optimization and some case study. In the second session, we will discuss about some multi-criteria decision-making methods. So proceed further to the first session before Madam will start discussing about the PSO and the case studies. So I'll introduce Madam. So Dr. Priyanka Chawla Madam is working as an associate professor in the Department of Computer Science Engineering, NIT Warangal. Her research interests lie in the area of cloud for computing, soft computing, and artificial intelligence. She has several publications in various reputed national and international journals and conferences. She is also editorial board member of many reputed journals. She is also the reviewer of many reputed journals and the member of organizing committee for several conferences and workshops. She is also a member of various reputed professional bodies like IEEE, ACM, IST, ISC, and other society. So, with this brief introduction, I request Dr. Priyanka Chawla, madam, to start the session. Madam, please.
Thank you, sir. So, good afternoon, everyone. Are you all able to hear me? Am I audible to everyone?
Yes, madam. Your slide is also visible, madam.
Okay.
Yeah.
So, today we will study about particle swarm optimization. So, this would be the outline. So, we will first discuss what is optimization. What do you understand by optimization and different optimization methods? And then we will start with the particle swarm optimization in particular. So, let's start. So before starting, students, what do you understand by optimization problem? Yes. What do you understand by optimization? Am I audible?
Yes, madam, you are audible.
Okay. So what do you understand by optimization problem? What is optimal solution? What is optimal value? So we'll start with the optimization problem. So optimization problem, we say it is a computational problem in which the objective is to find the best of all possible solution. Means in this problem, the main objective is we want to either find either a maximum value or the minimum value. Okay. And how do we define optimal solution? Optimal solution is the value, is the solution to the optimization problem which either minimizes or maximizes the objective function. And the third thing is, what is optimal value? Optimal value is the maximum or the minimum value of the objective function that we compute with the help of objective function. So this is like all the basics about what is optimization problem, its solution and value. Now let's see the optimization problem with the help of an example. You can see here I plotted the graph of this function y is equal to f of x. And this f of x is equal to sin x plus sin x square plus sin x and cos x. So what is the problem? Problem is to find out the global maximum and global minimum. So you can see here from this graph, like you can see here, there can be lot of local maximum minimum position, but there is only one global maximum. This is the global maximum value, and the global minimum value is this one. So there is only one global minimum and global maximum value. But if you take the case study, like if I take the x-axis from -4 to 6, so what would be the, you see, what would be the like from -4 to 6, so what would be the local maximum? Local maximum will come out to this point. This won't be the global maximum. This is only the local maximum. So this kind of problem, when we have a lot of local maximum, we have a lot of local minimum, so we use the meta heuristic algorithm, or we say optimization algorithm. Okay. Now let's take the another example. This is the, you see, higher dimensional problem is there. So you can see here, if I ask you, you have to find out, this is the plot of this function z is equal to f of xy, and this is, we have to see here sine x, we have multiple variables, sine x square plus sine y square plus sine x and sine y. So here you can see, if we add more variables, now it becomes more difficult to find the global maximum and global minimum. So it can be any, you can see here. And now in this case, how to find the global maximum, global minimum? Because it may like suppose you're using some traditional optimization algorithm method, so it may lead to you a local maximum, local minimum. But the objective is to find the global maximum and global minimum point. So with this kind of problem, this optimization algorithm like PSO, it helps us a lot. So let's see what are the different optimization methods. So we can categorize into two types. The first one is the classic one, and the other one is meta heuristics based. So in the meta heuristic, we can have two type of algorithms. One is trajectory based, another one is population based. So in the trajectory based, you can say neighborhood based algorithms are there. For example, neighborhood algorithm like simulated annealing algorithm is there, taboo search is there. But if we talk about population based algorithm, there we have the another, we can divide it as the another category, that is nature inspired. So in the nature inspired, we can have two categories. The first one is evolutionary algorithms, and the second category is swarm intelligence. So in the evolutionary algorithm, genetic algorithm will come into the picture. So I think genetic algorithm you have already covered. Whereas if we talk about swarm and intelligence, so particle swarm optimization would be there, and colony optimization would be there. Bacterial foraging algorithm would be there, honeybee algorithm would be there. So these are all population based algorithms, swarm intelligence. Now next is,
Hello.
yes.
Ma'am, sorry for interrupting. This is Mustafa Shamim Firdaus. I'm a community scholar. Would you please be kind to go to the previous slide, please?
Yes.
Ma'am, what is the basic difference between these evaluationary algorithms and swarm intelligence? I mean,
What is the difference between evolutionary and swarm intelligence? Can you please
I mean,
repeat your
what is the
question?
difference between the two? I mean, in the nature-based, in the nature-inspired algorithm, we're finding that there are some algorithms which is being classified as evaluationary algorithms, and on the other hand, some is classified as swarm intelligence. So, ma'am, what is the basic difference between these two?
So the basic difference, as from the name, you can take evolutionary. Evolutionary means which is based upon the evolution of, like, suppose genetic algorithm. What do we have in the genetic algorithm? The operators are different. There we have like chromosomes are there, okay, and there is a mutation operator. Then we have a crossover operation. So it is based upon the evolutionary principles. Whereas if we talk about swarm intelligence, so swarm intelligence means they are group of people, like we have birds, group of birds are there, group of fishes are there, how they search for their food. So swarm intelligence algorithm, they are based upon like how group of particle or group of uh, individuals, they help each other and they search for a particular target. Like you can see here, we will discuss in the particle swarm optimization, that is, it is inspired by the birds, like how the birds, group of birds, they look for their food. And ant colony, you have studied yesterday, I guess. So ant colony, they like how the ants, they communicate with each other and they learn from each other. In the same way, in particle swarm optimization, there would be different individuals and they would be communicating with each other, and they would be in this way, they would be helping in each other in learning, like how to find out their food source. Whereas if we talk about evolutionary algorithm, that is only like it is, the principle is different. So it is based upon the principles of evolution, like how the generation to generation changes has been done. Okay, only operator kind of difference is there.
Okay, ma'am. On the previous slide, please. Just another question is there. Yes. So, ma'am, I mean, these sort of group activities by the animals, okay, or yes, by the living beings in the nature, we do classify them in the swarm intelligence. So, the BAT algorithm, I mean, it is swarm intelligence, or right?
Yes, yes. So
Okay.
let
So,
me first explain particle swarm optimization, then you clearly understand like how it is different from the evolutionary algorithms.
no, ma'am. My simple request to you is that there is an algorithm. It is called actually BAT algorithm. BAT algorithm. The bat actually, they move in the night. Okay, they don't see. So I mean, simply like the sound, by actually passing the sound, they get the echo and they move. They fly.
Yeah.
So BAT algorithm is classified as swarm intelligence or evolutionary
Swarm,
algorithms.
swarm intelligence.
Okay,
Like
thank you
they
very
like
much, ma'am.
suppose they're group of individuals, they are communicating with each other and they're also learning from each other. So such kind of if there is such kind of strategy, we categorize that swarm intelligence, communication
Okay,
and learning.
okay. So, ma'am, I mean, this population based is clear to me. So, what is trajectory based?
Trajectory based, like you might have heard about simulated annealing algorithms are there, taboo search algorithms are there. So they come under
Yeah.
this, or we can say neighborhood based algorithms.
Okay, so Rao algorithm is also trajectory based,
That you need to
ma'am.
look into that. Yeah. So let me I'll
Thank
be
you.
explaining all these things, okay, in my next slides.
Okay,
Let me
thank you very much.
complete
Thank you very
first. Now, next question is that, like, why do we go for, so you might have heard about deterministic algorithms. Deterministic algorithm, have you heard, students? So conventional optimization algorithms, they were deterministic algorithm. There were some limitations. What were the limitation? Like it was having only single base solutions, or they converge to local optima. Like if we have more than one local maximum or more than one local minimum points are there, like I shown you with the help of a graph. So they convert deterministic algorithms, they will only get you a local optima. You won't be able to get a maximum optima. Global optima. So to overcome these limitations, so several meta-heuristic techniques are there. They have been, we have used meta-heuristic techniques. So for example, particle swarm optimization is there, gray wolf optimization, and colony optimization, genetic algorithm. So they are all, you can say, meta-heuristic based algorithms. So what do you mean by meta-heuristic and heuristic? This may be another question that may arise in your mind. So any idea what is the difference between heuristic and meta-heuristic?
Actually, Honorable Professor Dr. Manjubala ma'am, she actually provided us lecture yesterday, and I asked her this question to be precise, and she replied to that question that in the meta-heuristic we have the freedom to actually search for the global optimization. But
Yeah.
in the heuristic, there are some issues. That's why, our algorithms sometimes get confined to the local, optimization.
Yes, exactly. So we can say a heuristic is a technique which helps you to solve a problem at a faster rate. Like where the traditional techniques are slow, but if we go with the heuristics, it will help us to solve the problem at a faster rate. But if we talk about meta heuristic, it is higher level technique, or you can say it is a heuristic that would provide a sufficiently good solution, or you can say global solution you'll be able to get. Better solution than the heuristic. And heuristic, what do we have in heuristic? We use some particular guess to guide the search. Whereas in meta heuristic, it is heuristic about heuristic. Heuristic about heuristic means we're going to refine our guesses also. So here we use only one guess in the heuristic. In meta heuristic, we are going to refine our guesses also. So that is why we say it meta heuristic. That is why it helps us to give the better solution to the optimization problem. So meta heuristic are like, we can divide into two parts, like the same question Shamim was asking, population based algorithm, and another one is neighborhood based algorithm. They are also called trajectory based algorithms. So population based algorithm, if we talk about evolutionary computation and swarm intelligence will come into there. Whereas you can see here, these are the example of swarm intelligence based algorithm. This cuckoo search is there. Then we have firefly algorithm, bat algorithms, honeybee mating optimization algorithm, frog leaping algorithms. So they are all swarm intelligence based algorithm. But if we talk about neighborhood based algorithm, or we call trajectory based algorithm, so there comes into the picture simulated annealing and taboo search. So these are about the basics. Now let's talk about the particle swarm optimization. So you can see here particle swarm optimization. It is the popular meta-heuristic method. So you can see here where there are two pictures. This is the picture of birds. You might have seen like birds, what they do actually. They make a group and they fly together. So you might have seen patterns like this in the sky. Have you ever noticed such kind of patterns of birds? So birds, they always they fly in a group in this pattern, similar or maybe the different pattern. And this right side picture show how the fishes, a school of fishes, they move together in a group. Like suppose they want to search for a food, they will not go alone, they will move in a group. So such kind of pattern they will form. So particle swarm optimization, it is inspired by the social behavior of birds and fishes. Okay, and it was proposed, this algorithm was proposed by James Kennedy in 1995, I never heard. And you can see here in this particle swarm optimization, it combines the self experience of the bird and the social experience. It means the way how they are going to move, they are going to communicate with each other and they will learn from each other as well. So they will not move in their own direction. In the same way, fishes also move like this. So they combine the self experience and the social experience. Is it clear?
Ma'am,
yes.
The previous slide, please. Would you please be kind to repeat once again, please?
Yes. So particle swarm optimization, it is inspired by the social behavior of birds. So you can see the left side picture, it's the birds. So you might have, I don't know whether you might have seen the birds, they always fly in group. Have you ever seen? They make a beautiful patterns also.
Yeah, ma'am.
Have you ever observed? So this particle swarm optimization, it is inspired by the social behavior of birds. And the right hand side, this picture shows it shows small fishes in the sea. So there is a person. This is the sea diver. So you can see, and these are the fishes. So the fishes, they also move together. And particle swarm optimization is based upon these two the strategies of birds and fishes. So what they do actually, they combine their self experience along with the social experience, means they will learn from the experience from their colleagues also, from their fellow birds. So they will not move alone, rather they will move in a group and they will learn from the other birds also. In the same way, fishes will also, they will combine their own experience with the experience of fellow, you can see their friend fishes, okay, their colleagues. Clear? Is it clear
yes,
now?
Ma'am. Yes, ma'am.
So in a particle swarm optimization, so what is the meaning of word particle? So particle represents the potential solution. So you can see here, this is also, yeah, you see the birds, actually this picture shows the birds, group of birds, they're flying in the sky. So how do we define a particle? Particle represents a potential solution. So each and every bird, they represent a potential solution. So they move in the search space according to their own velocity, and they combine the self experience with the social experience. So you can see here, so I will explain this vector representation in my next slide. But as of now, you just have to just understand that they move in the search space based upon their velocity. Okay, and it is combined with the self experience and the social experience. And the optimization process, it will continue until the swarm converges to a satisfactory solution, until they find the source of food. Like suppose all these birds, they're flying together. So when they will, the success would be the one when they are able to find the food source. Okay, or like if we talk about, if we want to implement the particle swarm optimization, so what is the ending criteria? Ending criteria is either it converges to a satisfactory solution or it reaches a stopping criteria. Like you can specify the maximum number of iteration. Suppose you define, okay, only 100 times I am going to execute the algorithm. So if it is executed 100 times, it means the stopping criteria has been met. So you will stop there. Is it clear? So this algorithm, it is, yes, please.
I mean, the explanation, would you please be kind to explain once again, please?
Pardon?
I mean, would you please be kind to explain this slide once again, please?
Previous slide.
Yes, ma'am.
Yes. So
Yes, ma'am.
what you want me to explain? Like
I
how the
mean,
optimization process?
Yes.
So optimization process means, like you can see here, if the group of birds, they are flying together. So when will they stop? Obviously they will stop when they find the food source. Suppose they find the food, everybody will eat, every bird will eat the food, and then they will be dispersed. Okay, but if we say, like suppose you are implementing a particle swarm optimization to solve a particular problem, so what would be the like criteria? Ending criteria would be the either you converge to a satisfactory solution. Like I gave you an example of a bird, the bird, they are able to get the food. And if we talk about the problem that we are going to solve, suppose we have found the maximum, you have find the global maxima or global minima, so it will stop at that point. Or the other stopping criteria is when the number of iterations has been exceeded. Like, so we'll be discussing about this in my next slides. I'll be telling you, like, whenever we talk about particle swarm optimization is the stochastic optimization algorithm. So here we need to execute the algorithm more than once. So one or two iterations will not, we do not execute only once. So there are number of iterations. So we have to execute the same code more than once. So number of iterations may be 100, 200, 500, 1000. So that, suppose we have defined I'm going to execute my PSO 1000 times. So that would be the ending criteria. Suppose you have executed your PSO 1000 times. So there you're going to stop. Okay. So
Okay,
shall I move?
Please.
So this algorithm, like we say, particle swarm optimization algorithm mimics the cooperative and exploratory behavior of the swarms to search for the optimum solution in the higher dimensional search space. So it is just like it will work based upon the strategies used by the birds, how they work together and they find the food source. So it has been applied, PSO has been applied to wide range of optimization problem, like in machine learning for using function optimization, you can do feature parameter optimization, feature selection, in the clustering, in the engineering design, in robotic system control systems we can use. And it has been widely adopted and developed in various fields, and it has undergone numerous modification and improvements. So we are going to discuss the basic algorithm, but you can modify it as per your own problem that you want to solve. So we have, like, the researchers, they have proposed several variations of the original PSO algorithm, including like they use dynamic and time varying parameters. So they have used the multi-objective optimization for this particle, and you can also hybrid, like you can hybrid particle swarm optimization with the genetic algorithm. So hybridization, it's also been like hybrid versions of the PSO has also been formed with the other optimization algorithm. Another thing is why it is very popular, because it's very simple. So we'll see like how very few parameters are there, and velocity updates and distance updates. So we'll be discussing that. So you will find it's very simple if you compare with the other algorithms, and it is very efficient. And the same time, it is very flexible if we compare to the traditional optimization algorithms. So that's why it's very popular. So let's see the components of particle swarm optimization. You can see here in the left side, this is pigeons, they are flying together. And here, in the second part of this picture, I'm so showing you the different thing, like current motion part is there. This is the bird. So its location is xt. And this is the current motion part. You can see, you can say the velocity at which this bird is actually flying. And you can see here, this is the cognitive part. This vector represents the cognitive part. So this is the another bird. You can see another bird, and it will like how it adjusts its flight. So this is what we are going to discuss in this day. So there are different components. So the first component is particle. Okay, each particle in the swarm, it represents a potential solution. Like each and every particle means each and every bird. Okay, it represents a potential solution to the optimization problem. Second component is velocity. So velocity of each particle, it represents the direction and the magnitude of its movement in the solution space. Like suppose if we talk about a bird, so velocity means in which direction this bird is moving and what is the magnitude of its movement in that particular solution space. So this is velocity. And each particle, like, or we say each particle or each bird, so they will like adjust its flying according to its own flying experience and as well as the flying experience of other particles. Like suppose this is the bird, so it will fly according to its own experience as well as the experience of another bird. So this is how they adjust the values. So you can see here, suppose this is the initial velocity VIT, and you want like how this VIT plus 1 has come into the picture. So first thing would be its own personal best. So it will compare its position with the previous position. Like suppose this position, previous position, and this is the new position. So it will compare. How it will compare? It will compute the fitness of each and every value. So we'll be discussing with the help of example. So just just see that how they do the things. So based upon its own experience, so it will adjust its pace along with the experience of the fellow particles. So another thing is fitness function is there. We are going to use the fitness function. So this is the scalar function that would evaluate the quality of each solution. Like suppose this bird is there. So whether this bird position is good or bad, who is going to decide? That fitness function will tell us whether this position, the current position is good or not. And the objective of PSO is to find the particle with the highest fitness value. Okay, and fitness function can be defined as the objective either to be minimized or maximized depending upon the type of optimization. Suppose if you want to find the global maxima, so it means your fitness function should always be the maximum value, then only you will say it's the best solution. And if you want to find the global minima, so it means your objective function should have the minimum value. So these three components, they will work together to guide the particles in the swarm towards the optimal solution. And the optimization process, it continues until the swarm converges to a satisfactory solution or reaches a stopping criteria, and what is the final result? Final result is the particle with the best fitness value. So this represents the optimal solution to the optimization problem. So you can see here now, I'll explain this. So this diagram, the B part. So each particle you can see here, this is the cognitive. One part is the cognitive part, another part is the social part. Social part means it will be influenced by the fellow, like suppose this is a bird. So its personal best, it will compare with its current position, it will compare its current position with its previous position. So that is its own experience. So suppose the previous position was better. How are we going to decide previous position is better? We are going to evaluate the fitness of the previous position. If it is like suppose if it is like we going for the like minimization problem. So the fitness function gives the lesser value. It means the previous position was better. So this is called the self experience. Okay, and the social experience means it will take the inputs from the fellow colleagues also. From its colleague, like suppose it will evaluate its current position, it will compare the current position with the current position of the fellow. Like suppose the fitness value of the fellow bird is lesser, so it means that bird is having the better position, so it will adjust its momentum accordingly based upon the cognitive part and the social part. So this is xi t plus 1. T plus 1, T means, what is the meaning of T here? T means iteration. Suppose initially xi t, and in the next iteration it will change its direction based upon the personal best and the global best. So this is the global best, means the best position of all these parts. Like suppose there are 10 particles, 10 birds. Suppose among the 10 bird, one bird is having the best position. How we decide it is having the best position? The fitness value will be the lowest one. Okay, so that will be the personal. That is called, we say it is the, and that part is social part. Another one is personal best. It compare its position with its previous position. So that is cognitive part. So based upon these two parts, it will make the x. Now this is the xi t plus 1. Okay, so this is how it adjusts it makes the moves. Is it clear? So let's have a look on the basic algorithm of PSO. So what is the first step? We initialize the swarm from the solution space. Then we evaluate the fitness of each and every particle. Like, so we initialize, suppose there are 10 birds here. Okay, and we'll give some random positions over there. Second would be, we will evaluate the fitness of each particle, means evaluate the fitness of each and every bird. So we will evaluate whether which bird is having is at the best position based upon the fitness function. Third is update individual and global best. So you have to find out the personal best of that particular bird and the global best. Global best means, like suppose if there are 10 birds. So what is the best position among those 10 birds? So that will be the global best. After that, we will update the velocity and position of each particle. Fifth step is go to step 2 until some termination condition is, or repeat until the termination condition is there. Like suppose you can define the termination condition. Like suppose a number of iteration can be the termination condition, 100 iteration or maybe the 1000 iteration. So this is the basic algorithm. It's very simple. You can see from here. So this is the flow chart. You start, initialize the position and velocity of each particle. Next step is evaluate the fitness value of each particle. And for each particle, set local best fitness. Okay, that would be the current fitness and local best position. So you say the current position. Then we set the global best position. Then we update the velocity and position of each particle. Then we evaluate the fitness of each particle, and then we compare the current fitness. If it is lesser than the local best fitness, then we can update the local best. So local best would be current fitness. So again, we will find out whether the current fitness is less than global best. If it is yes, so we'll change the global best also. Okay. And if it is no, then we update the velocity and position of the particles. And after that, you can see if it is lesser than this, then we you see we update the global best, and if the stopping criteria has been met, yes, then we stop, otherwise you repeat these steps. Okay, so this is the flow chart. So let's see particle swarm optimization. So these are the things that we need to initialize. The first thing is swarm. Swarm is the set of particles. And next in this swarm we have a particle, and each particle represents a potential solution, and each particle would be having certain position and velocity. So this is the position vector and this is the velocity vector. So what does it represent? I1, I2, I so on to In. So it means n particles are there and the corresponding velocity of each and every particle. Another thing is each particle, it will maintain individual best, that is called particle best, and the swarm will maintain the global best. Whole swarm will maintain the global best. So how you're going to find out whether it is global best or individual best? With the help of fitness function. So you're going to evaluate the solution with the help of objective function or fitness function. And if it is only, you see the minimization problem, then if you are working on the minimization problem, the objective function, if it gives you the minimum value, it means that is the best value. So let's see the velocity update equation. So in the velocity update equation, there are three parts. The first part is called inertia part. Second is called cognitive. Third is called social. Cognitive means based upon the individual best, personal best. And social is based upon the global best. So VIK plus 1 is omega into VIK. This is the inertia. Initial, like the velocity at which the particle was initially flying. Plus cognitive part, what is having the cognitive part? Here we have two constants, C1 and this is the random number that we generate, into the subtraction of particle best and the current position of the particle. Plus social part, we have C2 and R2, another random value. So it will be having the difference between the global best and its current position. Okay, and what is W, C1, C2? They are constant values. And what are random 1, random 2? They are random variables. So they are generated. Generally, it is between 0 to 1. And this is the position update. You can see xik plus 1 would be depending upon its previous position xik plus the vik plus 1. So this is how we compute the vik plus 1. Okay, so let us understand how these vectors work, like how to compute the velocity and how to compute the distance with the help of an example now. So it will be more clear. Like,
Ma'am,
yes.
What is inertia in that equation?
What is?
Inertia.
Inertia, I'll explain, don't worry.
Okay, ma'am.
So let's understand how the solution update is happening in two-dimensional. So you can see here, this is the workspace I'm showing you. And this is the like xk, this is the current position of the particle. And this x, this is the particle best position. And this is the global best position yk. So I have initialized xk. Now suppose the xk current solution is having 4, 2. You can see here from the grid also. This is the x component is 4 and y component is at 2. Suppose the current solution is 4, 2. And the value of particle best, suppose I've taken it 9, 1. So 9 is the x value and y is 1. This is the position of particle best. And the global best is at, suppose it is at 5, 10. The location of global best is 5, 10. So let's see how the updates take place. Now suppose I've taken the inertia value, that is Vk, as minus 2, 2. Okay, and what is the meaning of this inertia? I'll explain you in the upcoming slides. But just understand how these solution updates are happening. Suppose the inertia value is minus 2, 2. Okay, this I have taken the inertia value. You can see here. This is the inertia. Inertia is actually the, like suppose suppose there is a particle there, or you can say suppose there is a bird and bird is flying a particular speed in the previous iteration. So that is called VK or inertia, like the original speed of the particle or the bird. Now suppose this is minus 2 or 2. Now let's see how the solution gets updated. So inertia is this. So first we will evaluate the cognitive part. So how the cognitive part is evaluated? So it is personal best minus the position, current position of the particle. Personal best we have assumed that it is 9.1. So 9.1 minus this is the current solution, current position 4.2. So what we will get 9 minus 4, 5. 1 minus 2 you get 5 minus 1. So this is your cognate. This is how you evaluate personal best. So personal best would be 5 comma minus 1. Coordinates of personal best would be this. Now let's see how the social component is evaluated. So it is the subtraction of global best minus the current position. So global best value we had taken 5 comma 10 and the current position value is 4 2. So if we subtract 5 minus 4 it becomes 1. 10 minus 2 it will become 8. So this is the social component. So I told you in the velocity there are three components. The first component is inertia, second is cognitive, and third is social. So this is how we have evaluated all the three components. Now next comes part to how to update the velocity update, how to do the velocity update. So VI k plus 1. So here you will add the inertia value. Inertia was given to you minus 2 2 plus here this is the constant value C1. So suppose I have taken that constant value as 0.8. In multiply by the cognitive part has come out to be 5 comma minus 1 plus this is the C2, another constant value 0.2. Multiply by the social value that comes out to be 1 comma 8. So you get this updated velocities VIK plus 1 is 2.2 comma 2.8. Now based on this we have to do the position update. So how we are going to do? So this is the formula for the position update. Xk plus 1 is equal to initial position plus the velocity Vk plus 1. So initial position of the particle was 4 2. So you will just add with the Vk plus 1. Vk plus 1 we just computed as 2.2 comma 2.8. So you will add it component wise 4 plus 2.2. So it will come out to be 6.2. Then 2 plus 2.8. So it will come out to be 4.8. So this is how you see how simple method addition operation we have applied. Simple addition and subtraction operator we have applied and we have found the new position xk plus 1. Okay, is it clear? Solution update. Have you all understood this example, students? Now let's see the instinct, understand this algorithm, each and everything. So we have seen that in this algorithm, the movement is towards the promising area to get the global optimum value. And each particle will adjust its traveling velocity dynamically according to the flying experience, its own flying experience, plus the flying experience of its colleagues. Okay, that's why there were three things in the velocity. Inertia was there, then we have this personal experience, then the third was the social experience. Each particle, it tries to keep track of the personal best and the global best. So I have shown you that this is the important thing. And then each particle modifies its position according to its current velocity and then current position. The third thing is the distance between the current position and the particle best and the distance between the current position and the global best. So here you can see here, so this is the difference between the global best and the current position, and this is the difference between the, you see the particle best position with the current position. Okay, so there are three things, this we have seen. Now let's take one working example. So we will execute the algorithm by taking this is the objective function I have taken. F of xy is x minus 3.14 raised to power 2. Then y minus 2.72 whole square sine 3x plus 1.41 plus sine this. You can see this is the very This is your objective function, and this is how it looks like. So problem is that you have to find the global optimum value here for this function. Okay, so let's execute the algorithm. The first step is create a population of particles. Okay, how we are going to create a population? We randomly give the position to each and every particle. Second step is evaluate each particle position according to the objective function, and this is our objective function. So we're going to execute the PSO algorithm, and the objective function is this for this objective function. Now third step is if a particle present position is better than the previous best position, then you have to update it. Okay. Then fourth step is find the best particle. This best particle is the global best particle. Fifth step is update the particle velocity that I've shown you with the help of example how we update. So this is Vi t plus 1. This t plus 1 is the iteration number. T is the iteration number. And I represents the number of particles for each and every particle. So there are three components here. The first component is the inertia component. Second is the, you can see here, this is the, you can see personal best, self-experience. And the third is the social experience. Or you can say the second component is cognitive and the third is social one. Then move particle to the new position. This is the position update formula. Position update is the previous position plus this velocity value. And you have to repeat these steps from, you have to start again from 2 and until the stopping criteria is met. So you can see here in this, yes.
In the previous slide, actually, how to conclude how many particles will be there?
So
It's
you
a
randomly,
yes.
we are going to, like suppose this is, you are going to, I will show you with the help of example, either you can take 10 particles or you take 100 particles. So it is better to have a large size population actually. Suppose you want to solve a problem. So it is always better to have a large population size. Like 1000 population size would be better than the 100 population size. And 100 population size would be better than the 10 population size. That you have to decide what would be your population size.
One more question I have actually. Initially, you have to
Yes, please.
set a global optima. It's not in them to fit the formula
No,
here. Means,
we have
but
not set the global optima. The problem is to find the global optima.
means the equation 5, step 5, update particles velocity. In there, we have a global optimum value.
Step 5. Which step?
Yes, ma'am. 5, update particles velocities. There
Velocity.
C2, that is GB, that is global.
Yes, GB is the global best. It is not optimum value. It is global best.
I mean, that's what. Sorry, ma'am. For the first iteration itself, means we need to set a global best initially. We have to initialize something.
No. We are not going to initialize. We are going to compute it. So I'll show with the next.
Means without having GB, how can we compute? Means?
Yeah. I will show. Have patience. I'm going to show for this. I'm going
Okay,
to show how we are going to evaluate global best. How we'll evaluate particle best. I will show for this example only. Have patience.
Okay.
So we are not initializing here. Initialization is only here, the first step.
Yeah, means actually in this slide it is not initialized, but that equation makes some doubt for me. That's why I asked.
Doubt would be cleared. Let me complete this example.
Okay.
I will show you like how we are going to update the particle velocities. So global best we are going to compute. We are going to evaluate. In the same way, particle best we are going to evaluate. Okay. So how we are going to do that? So I will be discussing this. Okay. So suppose this is your, you can see this is the function, this is the objective function, and this function looks like a curved egg. Okay. And if I ask you, student, you tell me what is the global minimum value. So it would be really difficult for you to find out the global minimum value. Okay, because there are a lot of local minimum values are there. And those local minimum may not be the global minimum. For this kind of problem, so that is why I'm choosing the particle swarm optimization, because there are a lot of local minimum values are there, but I want the global minimum value. So how to do that? So I will apply the algorithm. So this is a contour plot of the same, you see the same function, contour plot of fn xy, and here I've given the bound of x is less than equal to 0 and y is less than equal to 5. This region I have defined. So initially I have created 20 particles. So you can see here they are blue dots. So they are 20 in number. Okay, and I have given the random position. This is the first step, initialization. I have initialized, I have decided my population size would be the 20 particles, and each and every particle I have given some random location. So these locations, blue dots, they are randomly decided what location they will get, all these 20 particles. So this is the first step, and this cross mark, it depends, like I'll show you. So position of G best is marked as a star. This is the global best position. Okay. So this I have marked as a star. So I have marked as a star only just to tell you how this PSO works. Now this is the position of particle after one iteration. So you can see here these blue dots, they have moved little bit. And how I've said C1, C2 is equal to 0.1. These are two you see constants, and W I've sent to 0.8, inertia weight I've sent to 0.8. Now next I will update the position and velocity according to the formula that we just discussed, and then we will update particle best and global best after that. And we here in this we have marked the best position of each and every particle as a black bubbles. So you can see very close to blue bubble, they are black bubbles. So they are particle best position, and this situation is after one iteration. Like if I move after two iteration, this is the position. So after two iteration, you can see here the particle, they have started moving towards the global best. This is the global best. So,
Madam, how to identify the global best from the contour plot, ma'am?
So this I've taken the example, and how to find out I will get after this. I'm going to discuss one numerical problem. There I'll be telling you how to find out. Okay. So please have patience.
Okay, ma'am.
Yeah. So this is the position of particles after 5 iterations. So you can see they have moved a lot to towards this global best position. And this is the position of the particle after 20 iterations. So all you see they have like found the global optima. They have found the position. So let's see with the help of this animation. So you see iteration are changing, iteration 12, 13, 14, 15, 16. After 20 iteration they almost achieved. So you can see some resemblance to the movement of flock of birds. So you can see here, they have found this value. So you can see here again. So resemblance is to the movement of flock of birds. So how it's moving. So you hear the iteration, they are changing and they are finding the global optima. So this is how it works. So this I've shown you with the help of simulation. Now let's discuss the parameters here. So this is the velocity value, velocity vector. So here you can see the parameter W is here. This parameter W is called the inertia weight, and this is the positive constant. It is always a positive constant. So this parameter is important if you like it. It is important to balance the global search, which is called the exploration. And when you set the higher value of W, that means there would be more exploration. And if you set the lower value of this W, it means there would be exploitation. So you have to adjust it little bit so that there should be a balance between exploration and exploitation. So what is this VIT? VIT is the VIT plus 1 is the new velocity in the new iteration. VIT is the velocity of the particle in the previous iteration. Okay, here, and you multiply this velocity value with the inertia weight. So this you have to, like, very intelligently you have to decide what should be the value, because if you take too high value, it will go for the exploration. It means it will fly in its own, suppose in its own way. And you keep, if you keep it low, so obviously if it is if you put more value to it, so it will make the particle move in the same direction with the same velocity. Same means the way in which it was moving in the previous iteration, so you're going to, like, giving more emphasis on that, so there would be more exploration. But if you set the lower value, it will go with the exploitation. So you have to keep a balance between exploration and exploitation. This is the first thing. It is also called diversification. So it searches new solution and find the regions with potentially the best solutions. Okay. Second component is the intensification. So in the intensification, the first we have personal influence, and the second is the social influence. Personal influence, it means it improves the individual, make the particle return to the previous position better than the current. So here you are computing the difference between the particle best and the particle's current position. Okay. And in the social influence, so it makes the particle follow the best neighbor direction. So there is a difference between global best and the particle best. So like suppose if you here in this, now we will discuss how to adjust the C1 and C2 parameters. Like if you take value of C1 too high, so it means you are giving more weight to the personal influence. If you're giving the more higher value to the C2, it means you want to put more weight on the social influence. So you have to optimally adjust the value of C1 and C2. And what is U1T and U2T? These are the random numbers. These are the random number. They're usually between 0 to 1. So you randomly initialize these. These are also the constant value, but randomly initialized. So suppose you have set W equal to 1 here. This is the inertia weight. So if you set W equal to 1, inertia weight 1, the particle motion would be entirely influenced by the previous motion. So it means the particle will keep going in the same direction. The same direction it is the same direction it is moving in the previous iteration, the same direction it will assume. Otherwise, on the other hand, if you take this W greater than 0 and less than equal to 1, so such influence you can reduce. So it means the particle instead goes to the other region in the search domain also. And the second parameter is parameter this C1. This C1 is there. So C1 is the individual cognition parameter. It weighs the importance of particles' own previous experiences. That is why we say it personal influence. So if you give more value to the C1, it means you want to put more weight on the personal influence of the particle. The other hyperparameter value, you can see which compose the product, it's the random number. So this random number lies between 0 to 1. So this random parameter, it plays an essential role in avoiding the premature convergences. Okay. And again, this C2 is the social learning parameter. This C2 value is the social learning parameter. And if you give more value to this, it means you want to give more weightage to the global learning of the swarm. And this U2, this U2 is the random number. So this is same as that of U1T. It also lies between 0 to 1. Now suppose if you put C1 is equal to C2 equal to 0. So it means the particle will continue flying at the current speed until they hit the search space boundary. Suppose if you put this C1 and C2 0, it means the particle's new velocity would be only equal to inertia weight multiplied by the initial velocity. So here it will just fly like that. No personal, it will not take any weightage from the social experience and the personal experience. In case if you put C1 greater than 0 and C2 equal to 0, it means the particles are independent because it's only taking into consideration of personal experience. No social experience, you make it 0 by putting C2 equal to 0. And suppose if you make C2 is greater than 0 and C1 is equal to 0. So here all particles would be attracted to a single point in the entire swarm. Here you are not giving any importance to the personal experience. And in case C1 is equal to C2, it's all not zero. They're not equal to zero. So particle, they are attracted towards the average of particle best and global best. So we usually give this like C not, it should not be equal to like optimum value we need to choose. Now let's see solve one numerical problem. Like a lot of students, they have questioned how the global best values are computed, how the particle best values are computed. So that I will explain with the help of a Rosenbrock function. So this is the Rosenbrock function, objective function is this. And I want to keep the bounds like this. Less than xi should be greater than equal to -5 and it should be less than equal to 5. So let's run this algorithm. So you can see here, I've taken for this objective function, this is my initial swarm. So I have assumed the population size is 8. I've taken 8 is my population size. And this is the iteration number 1, initial iteration. So this is the index for each and every particle. This is the position vector of each and every particle. This you can see, I have randomly initialized it. And the initial step, what we do, I told you in the previous example also that the position vector is, position of each and every particle is randomly assigned. So these numbers, these position I have randomly assigned to each and every particle. Okay, initial position of each and every particle, and initial velocity I would all set to 0 because this is the iteration 0. So I set it to 0. Initial velocity is 0 for each and every. I have assumed this. Now this is my objective function. Okay, so for each and every, like suppose this is my first particle, particle 1, it's you see x1 is 2.212 and x2 is 3.009. So I have to compute the fitness of this solution. How we are going to compute the fitness? You put this x1 and x2 in this formula. So you will get, this is the fitness value of this particle. Fitness value, if you put this value in this here, you will get 357.154. So this is the fitness of the first particle. In the same way, the fitness of second particle will come out to be this. And for the third particle, you see it will come out to this. So I have computed the fitness of each and every particle here in this table. Is this clear, students? Are you all getting how we are computing the fitness value? The second step of the PSO is to find the fitness value of each and every particle. The first is we have to initialize, we have initialized the swarm and we have assumed there are 8 particles over there. And then we have given them the random initial positions. And then the third step, we have computed the fitness value of each and every particle. Is this clear up to this step, students? Yes, Dr. Arun Kumar.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Now let's see the another step. So here I'm going to evaluate the particle best. So this is the initial position that and this is the fitness of each and every value. And this third column, fourth column is particle best. So particle best, I'm going to, like you can see here, particle best would be the same as that of the initial position. Why? Because this is the first generation. So the local best or particle best would be the position of the particle itself. So you can see here, this is the particle best. It's the same as of the initial position. This P best is also same for the second particle. P best of the third particle is also same as that of the initial position of the particle. Fourth is also same. So this is the another step. We have computed the particle best. Is it clear? Particle best is same as that because since it is the first iteration, so we cannot compare it because there was no iteration before this first iteration. So we'll keep it same. Okay. Now next is we have to find out the global best of the swarm. So global best would be the minimum of all the fitness values. So you can see this, these are the particle, all the 8 particles are there. And this is the initial positions. And this is the fitness value. This we computed with the formula. And this is the local best. It is same as that of the particle's initial position. And this fifth column represents the global best. So global best, how we find out the global best? We'll compare the fitness of each and every particle. You can see, and we find out the minimum value, fitness value would be the global best. So you can see here, if we compare 357.14 with 5843, 1106. So minimum value in this column is 167.414. This is the minimum value. And the position corresponding to this minimum value is minus 0.639, comma 1.692. So this is my global best. So I have put all this value to for all the particles. This would be my global best. Is it clear how I've computed the global best in iteration number 1? Yes, Mr. Majumdar, Shamim.
Yes, ma'am.
Is it clear? So I have evaluated, very simple thing. I have compared the fitness of each and every particle, whichever particle is having the minimum fitness value. So I have taken the coordinates of that particle as the particle best position in the iteration number 1. Okay. Now next step is we have to do the velocity update. So velocity of each particle is updated using this formula. This formula we have already discussed. The first is inertia velocity. Then we have, this is the cognitive, or you can say personal experience. Third is social experience. So for this example, I have assumed the value of W is 0.75 and the value of C1 I have taken 1.5 and C2 I have taken 2.0. Okay, so let the random numbers for each and every particle, this I have randomly generated. Okay, by using any random number generator I have used, and it should be between 0 and 1. So these are my random number 1, this is the random number 2. So this I have randomly generated. So let's see how to find out the velocity value. So particle 1, its initial position is this. This I had initially, initially given randomly, this position was given. Initial velocity was 0.0. This I have initialized to 0. Now the third thing is local best. Local best is same because this is the first iteration. So you cannot compare with the previous position of the particle because this is the first iteration. So that's why I've taken the local best same as the current value of the particle. So this is same. These two vectors are same for the iteration number 1. And this is the global best. Global best we just computed. So that is the particle which is having the minimum fitness value. That coordinates I have put as the global best. And this is U1 value here 0.661. U2 is 0.312. So I will put all these values in this formula. So you can see this is the second velocity 2 for the first particle. So I multiply 0.75, the value of W here, multiply by 0, initial velocity is 0 here. So it will be 0. You can see VIT is 0 here, plus this C1 is 1.5 into, so you have to multiply by U1T, so that is 0.661, multiply by particle best minus, what is the particle best? Particle best is 2.212. And the position, initial position of the particle, first this one x1 is this is 2.212 plus this is the another value, C2 is 2, and then the random value for this is 0.312 multiply by global best. So this is my global best, 0.639 minus this position to current value. So that is 2.212, the first vector value. So it will come out to be minus 1.779. In the same way, you have to do for the x2 also, the same computation for the x2 part also. Okay, another part. So you will multiply 0.75 with the initial velocity plus C1 1.5 into this random number 0.661 and then the another value, the second component 3.009 here. For this minus 3.009, this is particle best minus the initial position of the particle plus C2 multiply the random number and then this this global best, the second component of the global best is 1.692 minus second component of the current position, that is 3.009. So it will come out to be minus 0.822. Is it clear how we have computed the velocity part, students? Yes, Mr. Majumdar.
Yes, ma'am.
Yes.
Clear, ma'am.
Yeah. So in the same way, we will do for the particle 2 also with the same values. For particle 2 also, you see initial velocity was 0 and the initial position, this was randomly initialized. We global local best will be the same. Global best, this is the minimum value. Then you apply the same thing and you will get this part. The first part 0.893 and the second part for the velocity would be minus 2.212. So this I have found for each and every particle, 8 particles, the first part of the velocity and the second part of the velocity. So I can put in this table like this. So for all the 8 particles, you can see this is my initial position and this is the velocity, velocity vector I find out. Okay. Now I have to find out position update. So position formula for position update is PIT plus 1 is equal to PIT plus BIT plus 1. Okay, so I needed velocity that I've already computed. So I will just, you see how we are going to do. You have to do the simple mathematics. 2.212 minus 1.779. So it would be your first component of the distance. Same way 3.009 minus 0.822. So you will get these values. Okay. Is it clear? I found the distance value. So you have to perform component wise addition over here. So you just add the initial, this is the initial position and this is the velocity. You just perform the simple, you see, addition operation, 2.22 minus this, and for each and every particle you have to repeat the same thing. So you will find this. This would be your new position vector. New position. Is it clear? How the position update has been taken place? Have you all understood, students? Dr. Arun Kumar, Majumdar, Shamim, Nilesh. Is it clear, students?
Yes,
Am I
ma'am.
Clear, ma'am.
Yes, ma'am.
So another thing that we need to hear in the beginning, I told you the limit on x position was minus 5 to 5. Now
Hello?
see here in the particle 3. So this
Ma'am, so
now,
basically the
yes,
thing is that we are simply going for the range. Right, ma'am?
yes.
Okay.
This is the another thing because the limit on x we have put, it should be like equal to or less than equal to minus 5 and 5. So what I have to do here in this, it is coming more than 5. You can see 5.893. So I have to keep in bounds. So we have to update this thing. So this would be my updated position vector of the third particle. So I want to keep it within range. So I will make it 5.000.
So ma'am,
Okay.
particle storm optimization is nothing but the range only, right, ma'am? So for that
It's
is the
not the
thing actually.
range. It's only part of the thing. How here I have not done anything about the range. You see here I have put a limit in the beginning of the question. I have defined that for this range I am going to do because there should be a definite range now. So there was one constraint I have put. So many things we have learned. It's not only range.
Okay.
So you see here. So you see here I have put the bound for this Rosenberg function.
Mm-hmm.
So this was the bound xi should be greater than equal to minus 5 and less than equal to 5. So we found the new position vector, but that was coming more than 5. So I have to keep it in bound. So that's why I updated that position. Okay.
Okay. Okay.
Yes.
Okay.
So
Okay.
why I've changed this vector to 5 point? I've changed to 5.0. Why I've changed to 5.0?
Because of the
That I'll
limit.
explain because limit on x2 we had set initially.
Yeah.
We had said that
Yeah.
it should lie between minus 5 to 5. So I have changed. Other position vector would be same because they are less than 5. Okay. Now the next step is you increase the next iteration by 1. So you see this is my new position vector that we have computed just now. For each and every particle, you have to compute the fitness of value. So you apply the fitness formula for objective function on these coordinates, and this would be the fitness values. You can see here. Okay. And again, velocity update for the second generation, you have to apply the same thing, the same steps you have to apply with same W is this, C1 is this, C2 is this. Now you have to do the same thing for the second generation. So now here the initial position for the first particle is 0.433, 2.187. This you computed. So I've written here. So velocity part was this. Velocity part also you computed. I have written over there. Local best, now here you see this is the new thing. Initially we have set the local best equal to the current position. Now the local best, how we are going to decide the local best? So we'll compute the fitness of the previous position and we compute the fitness of the new position. So previous position fitness value was, you can see here, I will show here. So previous position, the fitness value was, I'll show here. So you can see here in the initial, previous fitness value was 357. This was my initial swarm. Initial position was having the fitness value of 357. But by applying all these position updates, new position vector, I have got the fitness value has changed to 399. So it has increased from 357 to 399. So it will compare the fitness value of the new position with the fitness value of the previous position. So the previous position was having 357. So the fitness value, but the new fitness value is 399. So since the previous position was having better fitness value, so what we will do, we will local best of the particle would be its previous position only. So here we will make the changes. It won't be same. In the second iteration, we'll compare with its previous value. If the fitness of the previous value is lesser than the fitness of the current value, so we will make the local best would be the previous position only. So here the local best value vector is 2.21 to 3.009, and this is the current position. Current position vector and local best position, now they are both different. Okay. Now U1 is 0.217 from here. Next step is you have to find out the global best. So how to find the global best? To find the global best, you have to compute the fitness of each and every particle. So you can see here. So this is the fitness of each and every particle. So this is, you see the second particle, it will come out this. So the global best would be the minimum one. Again, the same strategy you will apply, it would be the minimum one. The seventh particle is having the minimum value, that is 153. Okay, so the position corresponding to 153 is this position, minus 0.590, 1.577. So this would be a new global best in iteration number 2. Is it clear, students? In the second iteration, the global, we have found the global best value. Global best value is the one which is having the minimum fitness value.
Yes, ma'am. 153.484.
Yes. So in the same way, for the second generation, we will find out the component of the velocity. First component and second component, the same formula we will apply and we'll get these values. Okay. Now after this, we have to find out the new position. The formula for new position is this. So you can see here, so how you're going to find out this position vector, 0.533 minus 2.083, you will get minus 1.649. In the same way, 2.183 minus 1.107, so you will get these are your another particle position. Okay. Now here you can see here particle number 3, particle number 6 and particle number 8. So they are coming out of bound. Why? Because one of the here in particle 3, the second component of this distance vector, it is coming more than 5. It is 9.827. So we have to keep it in within the ranges. So I will make it 500. In the same way, for particle cis, it is coming out to be 5.793. So I have to make it 5.000. And for particle 8, again, you can see here, this, it's coming, this is, you can see here, whatever is coming more than bound, so we have to keep it below 5. So you can see I have made the changes here. Okay, here I have made, there was a, it was 6.291, so I have to make them less than 5, so I have kept it 5.00. So all the, I have kept within the bounds. Now you can see here again the same step would be repeated. You have to compute the fitness of each and every new position. So if you put this in the formula of the objective function, so these would be the fitness value that you will find. Okay, and this is the fitness of the particle after first generation. So what was the fitness? If you compare the fitness value after the first generation with the fitness value after this second iteration, you can see the here the minimum value is 13.222, but in the first iteration it was only 153.484. So you can see here it is improving iteration. If you increase the number of iteration, so the fitness value of the particles, it is improving a lot. Okay. Is it clear, students? Have you all understood?
Yeah, ma'am, a bit.
Yeah. A bit? Why a bit?
Actually, I mean, it would be better if we could run it through the, application part in the software, so that.
Okay, now we will take the another example. Okay, so for that you will be, all of you open, go to your Google, you should do with me. The same thing we will execute, okay, PSO algorithm in MATLAB. So what you have to do, all of you, you have to type, you open this MATLAB online, go to the Google, in the Google, type MATLAB online, and you click this link, MATLAB online. So you can see here, you get here, the start using MATLAB online, click on this button. So you, like here it will ask you about your registration. So you have to, if you are not having any account, you just click here, create one. So you give your details and make your account, simple details. It will only ask about your email address and all those things. And then you'll get one verification email. There you can just verify and your link would be created. For me, it is already there. So just go through the MATLAB online. So you get this screen. Students, are you all doing with me?
Yes, ma'am.
Yes. So open the MATLAB online by clicking on the button. So here I'll take the example of Saphere objective function. I'm going to take the previous example we discussed with Rosenbrock function. So here in the MATLAB, so we will do the execution by typing the code. Okay, the same algorithm, we will write a code in MATLAB. And for here I've taken the Saphere function. So what you have to do, you have to create a file, you name it as sphere.m, and you write this function, sphere function. So I have defined a function z equal to sphere x, and z is equal to sum x dot raised to power 2. So what is the sphere function? I think you have already done, no, you already know the sphere function. Xi square, xy square, summation of xi square. So the same thing I have defined here in the MATLAB, z is equal to sum component wise exponential. Okay, so first define the objective function. So here I have defined the objective function of sphere. So you can define anything if you want to do. Now next thing is you have to write the PSO code. So are you all able to see my screen? So this is my PSO file here. We are going to write the PSO code. The first is CLC statement, then clear, close all. So first section is the problem definition section. So here you will define your cost function. So for cost function, I have defined sphere function. Okay. Then is number of variables, number of decision variables I have made it 5. Okay, like in the earlier example, there were only 2 variables we had taken, x1 and x2. Here I have taken 5 decision variables. Number of decision variable is 5. It means it will compute x1 square plus x2 square plus x3 square, x4 square plus x5 square. So number of variables I have defined 5. Variables, matrix size of the decision variable I have defined, you can see number of row is 1 and n-var would be the number of column. Where size is this matrix. Variable minimum, here I have also given the bounds. Like in the previous example, Rosenberg, the bound was between x1, x2, it should lie between -5 to 5. Here the bound I have given to -10 to 10. So this is the lower bound of the decision variable var min, and this is the upper bound of the variable. Is it clear, students? Problem definition section. So you just type this if you want to do it, just practice how it works. Are you all there? Yes, Dr. Arun Kumar
Yes,
Majumdar.
ma'am.
So another section is parameters of PSO. You have to define the parameter of PSO. So here max IT, number of iterations, maximum iterations I have kept 200. So you can keep it 500 or maybe 200 or 1000. The more the number of iteration, the better solution you are going to get. So this I have defined maximum number of iteration. Then the population size and pop, this is the population size I have kept to 50. So again, the population size should be as more as possible. Like if you have a population size of 100, so solution would be better than the solution that you are able to find with the population size of 50. So this for this problem I defined as 50. Another is my inertia coefficient. I have kept it to 1. Okay, so this is the damping ratio. This I will explain later. Let me make this as a comment. Damping ratio I will explain later. So this W I've kept to 1. C1 value I've kept to 2. So C1 is the personal acceleration coefficient and C2 is the social acceleration coefficient. This also I've kept to. Okay. Is it clear? Parameters of PSO. The second section is parameter. I've defined the parameters of PSO. The third is initialization. So I have to do the initialization. So I'm going to define the particle template. Okay. So here I'm defining the part position as to be the empty one. Velocity is also the empty vector. So this cost I also have defined empty. Empty particle best position I've defined it. Then particle best cost I've defined it empty. And there only I am creating the population array. So you have created this population array, particle equal to rep mat empty particle with n pop and 1. Okay, so you're going to create a population array. Okay, so the particle will look like there would be and like suppose the population size is 50. So you will get 50 rows and 1 column for the particle. And global best is I have kept it to infinity. Initially, I have kept it to infinity because I have to compare the global best. Next part is you initialize the population members. For this, I have applied the loop for I is equal to 1 to n population. Then you have to generate the random solution. So how you're going to generate the random solution? Here I've used the uniform random function. Okay, so I've given the these parameters as var min, var max. These are the bounds. Okay, and then the var size. Okay, then you have to initialize the velocity. So initially I've like in the previous example also at the initial iteration, so initialization of velocity was done 0. It was initialized to 0. Initial velocity was 0. So here also I have, you see, I've used the zeros function. I am initializing the velocity with all 0. Next is evaluation. So here I am computing the personal best value. You can see how I am computing the fitness of each and every particle. Particle I dot cost equal to cost function. Cost function is my sphere function. So in this I am putting the particle I dot position. So it will compute the fitness of each and every particle. Okay. Then update, next step is you have to find out the personal best. So the personal best position, you can see here, it would be same initially, it would be the same particle I dot position, and particle I dot best dot cost would be the particle I dot cost. Okay. Another is update global best. So global best, you know, we have to compare with each and every particle. Whichever particle is having the less, you see, the fitness value, that would be considered as global best. So you are comparing it with the global best dot cost. I have initialized with the infinity. Okay. So global best would be equal to, initially it would be particle I dot best. So there, next I've taken the array to hold the best cost value on each iteration. Best cost equal to, initially I've put initialized to 0. Now let's see the main loop of the PSO. So this is my main loop. Here it will move only for max IT. Max IT I have defined to be 100. Iterations I have defined 100 for each and every particle. Okay, update, you have to do the velocity update. So we have this velocity formula we have applied here. Okay, the same thing that we just discussed in the previous example. And this is the update position formula. Then evaluation, you are computing the fitness of each and every particle over here. And after that, update the personal best. So you compare with the previous iteration. If the previous iteration, in the previous iteration, if the this cost value was less, means if the fitness was less, so you will initialize with that value. Best position would be the previous position. Otherwise, if the new position is having the better fitness, so that would be the personal best. Okay, then you have to update the global best. So global best, again you have to find out, it should be the minimum of all the suppose there are 100 particles, so you have to compare the fitness of all the 100 particles. The minimum value, the particle whosoever is having the minimum fitness value, its coordinates would be the global best. Okay. Then here I've used you see the best cost vector. So here I'm initializing with the global best values. This I've used to display the iteration information. Okay. And let me make this also a comment. I will explain you later on, like why I'm using inertia damping inertia coefficient. So first, let us run this section. So, so I've run this code. You can see here, students. So let us see the particle best values. So this is my particle. So you can see here. So particle velocity, cost, and best vector, they're all initialized. So they are all initialized. This is the velocity vector, this is the cost one, and this is the, you can see, best value, position and cost. So you can see here, like I'm not getting so promising solutions. So what I can do, I can define this W vector I has defined one. So I'm going to define one more variable. This is called damping ratio of inertia weight. It means that each and every iteration, this inertia weight should reduce. So for this, I have written code over here. You can see here W is equal to W into W damp. So damp value I have initialized to 0.99. So you can see here in this code, I have written this damping inertia coefficient. Now if I run this value, this code, so you can see here, so there is little bit improvement. You can see a lot of improvement I have got. Now let me increase the number of iterations, students. So here I had defined the number of iteration was 100. Okay, so let me define it to 1000. Okay, and now I am running this code. So I defined the number of iterations to 1000. So you can see here in 1000, you can see this is the graph. This I have displayed with the help of, you see, so better result I am getting. So this I'm drawing with the use of this figure command, okay? And you can use this graph also, plot. Let me make it comment. Let's run this section. So this is your figure 2. If you use this, you will get this kind of graph. Okay, if you use semi-log so you will get the better presentation. Run this section. Okay, so in x-axis I have given the label as iteration, or on the y-axis I have given the best cost. So this way, like by modifying the objective function, whatever objective function you want to define, you can do. Now suppose if I increase the number of population size, maybe it's 50 here, if I increase to 100. So let's see what effect it makes. So I've increased the population size as well. So let me run this section. And let me show you the particle vector here. This is your particle. Now initially it was 50 by 1, now you have 100. So there would be 100 rows over here for the particle. So this is 100 particle. So velocity, position vector, cost vector. So everything you can see how you can vary it accordingly, according to your problem. The parameters you can change. So let me make it 100 and population size as 50. So student, have you all typed this code? Yes, have you all done this? Have you typed this code for the particle swarm optimization? First, you have to define the problem definition where you have to define your cost function, then parameters you define. Okay, then you initialize the things. Then you have to do the velocity updates. Compute the global best and the personal best. And then you can see the results with the help of a graph. And in the workspace, you can observe the value of each and every parameter. Like if I open this npop, so it will be showing that the variable value is 100. So I'm running it again. So this is my particle. You can see here, this is the particle. Are you all able to initialize the particle in the workspace, students? Are you all there? So I just hope you have understood this concept, how it works, particle swarm optimization.
Ma'am, please share the coding section. I'm traveling from my workplace to home now.
What you want me to share? Code?
Yes, ma'am. MATLAB code. Yes, ma'am.
Um,
Thank you, ma'am.
Students, if you have any doubt, you can ask me. So we have done two examples, two case study. One is for the Rosenbrock. So there we did numerical part. We have done by hand how the position velocity and how the global best and how the personal best is evaluated. The another example we did with the help of MATLAB code. Here we use the another objective function, that is a fair function. So we computed the same thing, global best, particle best, then velocity update, position update, by writing the algorithm in a MATLAB. So we just coded it for a different function. Is
Hello.
it clear? Yes, yes.
Yes, I mean, up to this is clear. But after the class, actually, I want to run this problem in my very own area of research domain.
Yes.
Okay. So in that case, some problem might come out. So that's why my humble request to you is that, with kind permission from the honorable organizer, sir and ma'am, may I be in your touch for further learning on this particular topic from you through email? Thank you very much, ma'am.
Yes, yes, you can contact anytime. In which domain you are in?
Ma'am, basically, I'm working in the field of financial engineering. So
Finance.
Yes, ma'am. So this swarm-based intelligence, it has some huge application in the field of supply chain, operation resource management, as well as in the finance.
Yes, yes, you can use there also.
Thank you very much, ma'am.
Yes. So student, let's see the applications of PSO where you can apply. In the function optimization, we have just seen the example like for the Rosenbrock objective function and for the Sapir function. So you can, it helps you to find the global minimum or maximum value. So you can use PSO for either a single objective or multi-objective function. And second application is in machine learning. So you can use this particle swarm optimization algorithm to optimize the parameters of machine learning algorithms. Like you can use PSO in this neural networks in sport vector machine in decision trees. And the third application is signal processing. So there also you can use the PSO to optimize the parameters of signal processing algorithms. In the control system, you can use PSO, like in robotic system, you can use in aircraft control system, you can use PSO, power systems, you can use PSO. In data mining, like Shamim, I think he's working in this area only. So you can use PSO to optimize the parameter of data mining algorithms, such as clustering, association rule, and feature selection. Okay. And for the image processing problem also, you can use PSO to optimize the parameters of like image processing algorithms such as image compression, image enhancement, and image segmentation. So you can see there are a lot of applications where you can use PSO. Now let's see the advantages. The first advantage is that it is very simple to understand. Only simple addition and with the help of simple addition and subtraction, we are able to get the particle best value, global best value, new position vector, and new velocity. Only by using the simple operations. Another is it's very flexible. You can see here you can handle either the single objective or multi-objective problem. You can use the PSO for the continuous and discrete problems. For the linear problem or non-linear problem, you can apply it anywhere. Okay, and it helps you to achieve global optimization. And it is very computationally efficient. Very low computational cost is there per iteration because the operation that we are doing, it's simple subtraction and addition. So it's very computationally inexpensive. So it's not, you can say, computational efficiency is there. And what are the disadvantages? Is the first disadvantage, it's very sensitive to the parameter. Like if you change the parameter value, like inertia weight, if you change, or the value of C1, C2, you will change, the output will drastically change. So it depends upon the inertia, these hyperparameters. So you have to very wisely, you have to decide the value of the parameters. Convergence speed, and sometimes it may be slow. So PSO may convert slowly in some cases, especially for the, you see, for the problems with the complex solution spaces. And these are the references. So this is the disclaimer. So thank you everyone. So I just hope that you are able to understand the concept of particle swarm optimization. If you have any doubt, you can ask me. So student, you have already done ant colony optimization and genetic algorithm, I think.
Yes, ma'am.
Yeah, now we have learned the particle swarm optimization. Can you just differentiate what is the difference between particle swarm optimization and genetic algorithms? What is the difference between genetic algorithm and PSO?
Ma'am, actually, PSO actually swarm intelligence, but that genetic algorithm, yes, it's also part of nature-based algorithm, but it does come. I'm forgetting. You have taught us on that. Slide number 7. I'm sorry, I'm forgetting it. But yes, PSO is actually a swarm intelligence based algorithm, But genetic algorithm it's not actually, swarm intelligence based algorithm, though it's nature based algorithm.
Both are nature inspired algorithm only. Genetic is also nature inspired, but it is based
Yes.
upon the evolution strategies. Like there we use different kind of operators. We have chromosomes are there,
Yes.
then
Yes.
we
Yes.
use crossover operations are there. The operation, you see, the operations are a little bit, if you compare with the operation of PSO with the genetic, the operation of genetics, they are little bit complex. 2 point crossover is there, then 1 point crossover is there, then you have to mutate also. Here the simple addition and subtraction operations are there. We have only used addition and subtraction, we are able to get the global best, particle best, velocity vector, new velocity vector, and new distance vector. Okay.
Yes.
And how it
Yes.
is different from the ant colony optimization algorithm?
And colony optimization algorithm is also, swarm intelligence, ma'am.
Yeah, it's also under the swarm intelligence. But what is the difference? Where you can apply ant colony optimization? Like suppose you want to find a minimum for the traveling sailband problem. There, ant colony optimization would be better. It will give the better result. Like if you apply particle swarm optimization on traveling sailband problem, you may not get good results. But if you apply a ant colony optimization to find the minimum path there, you see ant colony optimization, they have a benefit. So
Yes, ma'am.
like, yeah.
Yes, ma'am. Would you please be kind to share the slides with us, as well as it will be
Yeah,
very kind of you.
yeah, I will definitely
Please
share.
share your email address and your WhatsApp number with us in the chat window. Thank you very much, ma'am.
Okay. Any questions from the participant side? Yes, you may ask your question if
Ma'am,
you have any.
swarm intelligence.
Yes.
This swarm intelligence algorithm, we could run it through. On different sort of platform, like on Python as well, right, ma'am?
Yes, yes, you can write the PSO code in any language. You can write in either C, in C++, in Java, in Python. You can write. Okay,
Okay.
but in our today we
Any
discussed
applied
MATLAB.
kind of book on swarm intelligence, ma'am? Would you love to suggest us? I'm looking for applied kind of books where application through MATLAB, application through Python. These sort of things are available.
So you can just go through the references. I've shown you the references now. Like if you want to have more knowledge on this, you can go through these references.
Okay.
Hmm.
Okay. Thank you very much, ma'am. Thank you very much. So please be kind to share these slides with us,
Yes,
and
I
your
should
phone number as
definitely.
well as your email address kindly.
Yes, yes. Yes, any other doubts, students? Thank you, ma'am. Okay, thank you everyone. Thank you, ma'am, for giving me the opportunity. So we'll start our next session at 5:05. Thank you, ma'am. Okay,
Ma'am,
ma'am.
phone
Thank you.
number,
Thank
please, if you don't mind.
you. Yeah, yeah.
Thank you very much, ma'am. Thank you very much.
Good evening, everyone. Am I audible?
Yes, yes, you are audible.
Okay, thank you, madam. So I welcome all of you to the second session of today's program. So in this session, we are going to discuss about some of the multi criteria decision making methods. So we will basically see six different methods out of you can say 8 different methods. So we'll see each and every method with a numerical example. So I request all of you to do the hands-on calculation in this particular session. So we'll go for first what is the meaning of decision making, and we'll see the different types of decision making, and then we'll discuss about each and every method with the theoretical explanation as well as with an illustration. And I request you, as you are familiar with the MATLAB, because last couple of days you are learning MATLAB, so you can write the code the way you are writing simple program. You can simply write the code to run all the multi criteria decision making methods. So these are the things we are going to discuss in this particular session. First of all, we'll go for the process of decision making, and we'll see the different types of multi-criteria decision making methods. Basically, it is of two types, and we'll compare both type of methods. And then we'll see these are the different methods under multi-criteria decision making. And out of these methods, we are going to see 6 different methods out of 8 different methods. So we'll start with the weighted sum method. Is it is taking weight value as well as it is taking sum of the weight values, sum of the values, sum of all the criteria with their weight value. We call this method as a weighted sum method. Weighted product method is similar to weighted sum method, but instead of taking sum, here we are taking the product. Similarly, we have another method, that is preference ranking organization method for enrichment of evaluation, which is called as Promethi method, which is also a very popular method, because here we compare the values of one of the attribute with another value. And also recently we have published one article based upon the extended Promethi method or improvement over the Promethi method by applying the normalization technique. I'll tell you the solution while we are going to discuss these methods. Then we'll see another method that is called as Vicar. Okay, it is a Serbian term. That's why you can see it is written in Serbian, like BISC and something. It is written in Serbian term. It was developed by Serbian people. That's why it is mentioned like this. Then we'll discuss about one of the popular method that is called as TOPSIS, which stands for technique for order preference. Technique for order preference by similarity to ideal solution. That is called as TOPSIS method. Okay, so although the Mura method is there, but due to time limitation, I am not going to discuss about this multi-objective optimization using ratio analysis and analytical hierarchy process. These two methods, otherwise we'll see in one more lecture with their implementation details. And in fact, ASP is much more popular in comparison to all the methods. And there is another method that is called as analytical ANP, right? Is ASP. Another method is called as ANP. That is also a widely used MCDM method. Okay, and this method is also adopted in various domains, various applications, which stands for analytical network process. And the last method is based upon the matrix concept of mathematics. That's why we call this method as graph theory matrix approach, or we call that as a GTMA. Okay. So we'll start these methods one by one, and if you have any doubt, you can ask while we are discussing or at the end. So coming to the multi-criteria decision-making method. So is the term suggested, you have a set of criteria. You have two or more criteria. By considering these two or more criteria, you have to take a particular decision. So your decision is based on number of criteria, right? Suppose I will say, you can say it is criteria 1, criteria 2, criteria 3, up to let's say criteria n. Okay, all the criteria are may not be having same weight value. They may have different values, right? For example, if I am taking 10 different criteria, not necessarily each and every criteria I will give 0.1 weight, right? Because some criteria is more important to you, another criteria may be less important to you. Like if you go to a market, if you want to purchase something also, you have a lot of criteria. Once you can say one of the criteria, maybe you can say cost is one of the criteria, quality is another criteria, right? Like that, number of criteria we are considering. Based upon that, we are taking a decision whether to purchase a one product or other product. If you have multiple product while considering this MCDM problem, right? So this MCDM problem is divided into two parts. One is called as a multi-objective decision making. Another is called as multi-attribute decision making. So both are looks similar, and both case also we are doing the decision making only. But the type of problems, number of solutions, and values of the variable, if you consider, these two methods are different from each other. Like if I start with MODM, that is multi-objective decision method. If the problem is related to design, if you want to design a product or design a you can say product or a solution, in that case you can go for MODM method. But if you want to select, suppose there is a set of designs are there, and out of that design, if you want to select one of the design, then you can go for the selection based method. That's why if you go for a design process, design of anything, it may be software, it may be design of an instrument, it may be anything. So you have infinite number of solutions. There are number of ways you can solve that particular problem. But when you go for the selection based technique, this is finite solution, right? If you have 4 different alternatives or 4 different products, out of that you have to choose one of the product. That's why it is finite. And if you look into the variable, the MODM method is having continuous values and MADM method is having discrete values. So based on that also you can differentiate these two methods. But although these methods are actually MADM methods, whatever we are going to discuss, but in general in literature we call these methods are MCDM methods. In fact, you can say MADM methods are much more popular in comparison to MODM method. As MADM methods are better in comparison to MODM, so the term MCDM is dominated by the MADM. That is the way we are representing each method, or we say that these are the techniques, but actually they are multi-attribute decision making methods. So there are 4 different components if you want to focus when you go for MADM problem. In your respective research area, if you want to, let's say, if you have a number of solutions or number of things, and you want to select a particular thing, then you can apply the MADM methods, right? But there are 4 different components we are considering here. One component is called as the alternative. Okay, there may be a set of alternatives we have. These alternatives are nothing but a finite number of solutions. Okay, so for example, suppose I want to purchase a product from the market. Let it be the refrigerator, right? So if you found that there are 4 different type of refrigerator, I am representing it by R1, R2, R3 and R4. So these are the 4 different type of refrigerator. But how to choose one of the refrigerator out of these 4 refrigerator, that you can do by the help of this MADM solutions or MADM methods. MADM method will help you to choose one of the refrigerator out of 4 different refrigerator. How they are going to do? For this, you have set up attributes. For example, I am considering attribute 1, attribute 2, attribute 3, attribute 4. Suppose you have considered 4 different attributes. Like one attribute is cost, another is whether it is top load or side load. Okay. Sorry, you can consider that in the case of refrigerator, you can consider if there is a double door or single door kind of thing. You can consider energy consumption or power consumption. Okay. Or you can consider another is the liter, right? That is capacity, right? These are the 4 different attributes you have, right? Out of these 4 attributes, what you will do, you have to choose one of by considering 4 different attributes, you have to choose only one refrigerator, right? Or it may be a washing machine, it may be anything. Whenever you want to make a particular solution, you have to perform like this. So first one is our alternative. So this is our alternative. In each and every alternative, you will get a value for A1, you will get a value for A2, A3 and A4. Okay. Similarly, R2 case also you will get some values in A1, A2, A3, A4. But based upon your requirement, you have to select, right? Although you will get some, in some case the cost is better, some case the power is better, some case number of liters that can occupy it is more, right? So based upon that, you have to select. So attribute is the second one. Third one is the weight. Each and every attribute is having a weight value, right? For example, you can say for me cost is more important, so I can consider cost weight is, let's say, 0.5. Then number of liters is important, then 0.3. But you are less concerned about whether it is a single door or double door and power consumption, right? Like that, you can give a specific weight to each and every alternative. That is nothing but a relative importance of an attribute while you are making a decision, right? And these attributes are also again depend upon the user, right? Like your option, your choice may be different from my choice, right? So the weight value will vary with respect to different user. The fourth one is measure of performance of each alternative with respect to attribute. So these values, what you have with respect to the refrigerator and with respect to the attributes of the refrigerator, we call this as a performance measure. That is the performance measure of each and every refrigerator with respect to different attributes. So when you want to solve a MADM problem, first you have to focus on these 4 main components. Once you are ready with these 4 components, you can apply any MCDM or MADM problem, MADM solution to your problem. Okay, so proceed further. Let us start with the first method, that is called as your weighted sum method. Okay, these are the methods we are going to discuss. Probably next lecture we are going to see these 2 methods, Mura and AHP, and the implementation of these methods. Okay, so let us consider a problem that we are going to solve through the MADM methods, right? So this method, this problem is related to mechanical engineering, right? Especially cryogenic. It's a sub branch. So the question says that you have to select the optimal material for a cryogenic storage tank for transportation of liquid nitrogen for the data tabulated below. A particular problem is given to you for which you are given with the 7 different alternatives. So the alternatives are nothing but your rows. As I said, 4 components you have to consider. First one is called as alternatives, right? Alternatives are represented in the form of rows, right? And how many alternatives we have? We have alternative 1 to 7. Right? Now, coming to the second one, in this particular problem, what are the attributes or criteria? Criteria and attributes, attribute or criteria is represented in column. And if you see, the number of criteria is 1 to 4, right? 4 criteria are there. So what are these criteria? The criteria are toughness index, it is yield strength, and density and thermal, right? These are the 4 different criteria. So if you are non-mechanical background, then you can consider this as just a criteria 1 or attribute 1, and this is your criteria 2, criteria 3, criteria 4. And these are nothing but your alternative, right? This is, you can say, alternative 1, 2, 3, 4, 5, 6, and 7. So for each and every alternative, you have some value for each and every criteria. Like criteria 1 on your value, criteria 2 also your value, 3 and 4 your value. But these values may not be suitable for you, right? But these are the different alternatives available to make a decision, right? Now, if third one is our weight value, right? So if you see the weight value of criteria 1, weight value, it is 6. Criteria 2, the weight value is 2. Criteria 3, the weight value is 3. Criteria 4, the weight value is 1. Okay. But in the previous example, what I told you, if you go back to that slide, I told you first criteria is 0.5, second criteria is 0.1, third criteria is 0.1, and fourth criteria is 0.3. So if I sum these criteria, it is nothing but it is equal to 1, right? But if you go to this particular scenario, if I ask you to find the sum of the weight of each and every criteria, sum of the weights, then you will get it is 6, 2, 8, 3, 11, it is 12, right? It is not equal to 1. So what we can conclude here, that weight values, the sum of the weight values may not be, it may not be equal to 1. So if it is not 1, then you have to make it 1 by doing the process of normalization. So there are several methods of normalizations are there. I'll tell you one by one. So, okay, this is one part, and that is weight normalization is required in order to scale it this 12 into 1. And the fourth part here, that is called as your performance measure. So here if you check the performance measures values, performance measure values generally taken from alternative with respect to the attribute. So these are nothing but the performance measure values. Okay, just like it is a matrix, you can say, of size 7 cross 4, right? 7 different alternatives we have, 4 different criteria we have, right? So out of these you have to choose one. Okay, so let us start the first one. So if you apply the weighted sum method here, so the very first step of weighted sum method to identify that whether these criteria are beneficial criteria or these criteria are non-beneficial criteria, right? Beneficial criteria means, suppose if you consider profit, if profit is more, the result is better. If it is a non-beneficial criteria, if the value is less, that is better. So out of 4 criteria, maybe all of the 4 criteria are your beneficial, or it may be non-beneficial, or some criteria may be beneficial and some criteria may be non-beneficial. So if you see here, we consider that the first 2 criteria, right? If you consider TI and YS, that is toughness index and yield strength, they are considered your beneficial criteria. So we represent it by a up arrow, right? Just for notation purpose. There is no other meaning, right? So that you will know that if higher value is there, higher value is better. Okay. So, but if you go for D and T, that is your density and thermal case, the lower value is better. So these are called as non-beneficial criteria. So what is our objective? Our objective is nothing but maximize the beneficial criteria or beneficial attribute, okay, and minimize the non-beneficial attribute. Okay, maximize the beneficial one and minimize the non-beneficial attribute. Right. So this will also help you when you want to do a normalization. Also, you need to find whether you have to identify the higher value or you have to identify the lower value. That you have to actually know, right? So for example, if I ask you to find the best value for first criteria, so can anybody tell which one is the best value for first criteria TI? Out of this value, which value is better? Okay, or which value is the best for criteria 1? Can anybody say, or you can write in the chat box. Yeah, Nilesh sir mentioned it is 770. That is correct only, right? Because 770 is the maximum value, right? Maximum value is better because here it is a beneficial criteria. Similarly, YS case also, it is also a beneficial criteria because I have given an upper arrow, right? So if you calculate the maximum value, the maximum value you will see, here is 1365. Okay, so that you have to consider while you apply the normalization. But if you go for the density and thermal, these are called as non-beneficial criteria. As they are non-beneficial criteria, what you have to do, you have to choose their minimum value. So if you choose minimum value, the minimum value here it is 2.68, and here the minimum value I think it is 9.4. Yeah, it is 9.4. Right? So if I solve the problem here, okay, by considering this beneficial, non-beneficial criteria, so let me write here. These are the alternative 1, 2, 3, 4, 5, 6, 7, and attribute criteria C1, criteria C2, C3, and C4. So if the first alternative and criteria 1, if you see, it is nothing but 75.5 divided by 770. So in case of beneficial criteria, what you will do, you will divide the performance measure value. Okay, if the performance measure value is X, you have to divide it by X max for the beneficial criteria. But if it is a non-beneficial criteria, then you have to do reverse. That is X mean, minimum value you find divided by X. Because minimum value is the minimum among all. If I divide it, then the value will exceed 1. So basically we want to scale all the values in the range of 0 to 1. That is the reason for non-beneficial criteria we are doing X mean divided by X. So for C1 it is 75.5 divided by 770. Similarly it is 95 divided by 770. And third case is 770 divided by 1, that is 1. Fourth one, okay, let me write here, otherwise less space is there. Okay, C1, C2, C3, and C4. Alternative 1, alternative 2, alternative 3, alternative 4, alternative 5, alternative 6, and alternative 7. Okay, so first one, it is 75.5 divided by 770. This is 95 divided by 770. Next one is 770 divided by 770. Then 187 divided by 770. Then 179 divided by 770. 239 divided by 770. 273 divided by 770. Okay, these performance values I have, that's why I am dividing each and every performance value by 770. Next, I will go for the second column, right? That is your source, your yield strength, right? So for that, each and every value need to be divided by 1365. So it is nothing but 420 divided by 420 divided by, you will get 1365. Then 91 divided by 1365. 1365 divided by 1365. Then 1120 divided by 1365. Then 875 divided by 1365. 1190 divided by 1365, and 200 divided by 1365, right? And these are the beneficial criteria, right? That's why I used to represent by upper arrow. These are down arrow means non-beneficial criteria. So if you go for non-beneficial criteria, so the first value you can see here, that is 2.8, right? So you have to do non-beneficial criteria case, you have to take x mean divided by x. Okay, what is your x mean value? X mean value is 2.68. Okay, 2.68 divided by 2.8. So performance value is 2.8. Minimum value is in the numerator part, right? So again 2.68 divided by 2.68. Here it is 2.68 divided by 7.9. 2.68 divided by 7.9. 2.68 divided by 4.43. 2.68 divided by 8.51. 2.68 divided by 8.53. Okay, so in this way you can calculate a non-beneficial criteria. Similarly, if you go for fourth column, the minimum one is 9.4. Okay, so in the numerator part you have 9.4. Denominator part you will put the performance values. So I can write here 9.4 divided by 21.4. Then 9.4 divided by 22.1. 9.4 divided by 16.9. 9.4 divided by 14.4. 9.4 divided by 9.4. 9.4 divided by 11.5, and 9.4 divided by 19.9. Okay, so only difference is that for the beneficial criteria you have to take if you want to determine a value for the beneficial criteria, you have to take x is equal to x by x max. Okay, maximum value is always in the bottom, so that all the values will come in the range of 0 to 1. Similarly, if you go for non-beneficial criteria, it is nothing but x is equal to x mean by x. So this will give you in the range of 0 to 1. Okay, that is the reason why we do this type of normalization. Okay, so let us see what are the values we are getting. I have calculated. So yeah, I have discussed this one. Yeah, we did this one, this calculation, right? So after this calculation, if you see, yeah, these are the values you are getting. Now you can see in each and every column, you will get the values in the range of 0 to 1. And one value should be, at least one value should be equal to 1. So you can see here, in this column 1 is there, this column also 1 is there, here also 1 is there, here also 1 is there. What it indicates? It indicates that the value 1 indicates that that is the highest or lowest value in that particular column. As I said, these are beneficial criteria. You can say these are the positions where the highest value is there. If they are non-beneficial criteria, you can say these are the positions where you have minimum value. That's why now the value is changed to 1. Okay. So now what we will do? Now we have done the normalization of the performance values. But as I said, you also need the normalization of weights. So here if you look into the weight is 6231, right? Now I told you also the sum of the weight is not equal to 1. But if you do normalization, then all the values will come within the range of 0 to 1. Okay, so 6 plus 2 plus 3 plus 1, if you do, then you will get it is 12, right? So if you want to normalize, then the first value, this value is normalized as 6 divided by this sum value, that is 12. Here it is nothing but 2 divided by 12. This value is 3 divided by 12, and this value is 1 divided by 12. Okay, so you will see these values are in the range of 0 to 1, and if I sum these values, that is 6 by 12 plus 2 by 12 plus 3 by 12 plus 1 by 12, you will get the value is equal to 1. Okay, so first step is you have to normalize the performance values. Second step is nothing but you have to normalize the weight value. Okay, these two normalization is very much important, but now weight normalization is much more easier. But when you go for performance measure normalization, you have to think about whether you are doing the normalization of a beneficial attribute or you are doing for a non-beneficial attribute. That is very much important. Otherwise, sometimes you may commit mistake. If you take the highest value always, then you may get a problem for non-beneficial attributes case. Okay, or if you take lowest value, then beneficial attribute case you will not get the correct value. So you have to be first to see whether a particular attribute is beneficial or that attribute is non-beneficial. Based upon that, you can take a decision, right? Now you can see all the values are normalized in the range of 0 to 1. Whether it is a weight or it is a performance value, all the values are reduced to in the range of 0 to 1. There are quite a number of normalizations are there. Like you can go for min-max normalization also, which is a very popular normalization. Min-max normalization. So if you go for min-max normalization, it scales the values in the range of 0 to 1. But the problem with means and min-max normalization is that the lower value is now assigned with 0 and higher value is assigned with 1. Like here you can see the highest value is 1. It's okay, there is no issue. But if you go for the lowest value you are getting 0.098. But when you apply this min-max normalization, you will get this value as 0. So saying one particular attribute as 0 may influence your decision making process. That's why min-max normalization, while you are applying, you have to be very careful. Lower limit should not be equal to 0, right? There is another normalization that is called as Z-score normalization, or it is called as zero min normalization, right? That means if you after performing this normalization, if you sum all the values, that value is equal to, if you calculate the mean of that particular value, okay, then you will get all the values is equal to 0, because you will get some value as negative value, some value you may get positive value. And this normalization takes mean and standard deviation into picture. Both mean and standard deviation it takes into consideration and apply the normalization process. Then another popular normalization is there, that is called as your decimal scaling normalization. So in which what we are doing, we are finding a value which is greater than all the performance measure, and that value should be 10 to the power something. For example, if you go back to this particular slide, okay, now you can see all the values, the highest value in this particular data which is present in the table is 1365, right? If I have to choose a particular 10 to the power, okay, a 10 to the power something, such that 1365 is less than 10 to the power something. So if you take 10 to the power 4, this condition is not 10 to the power 3. Okay, 10 to the power 3 means it is not satisfied. 10 to the power 3 means 3 zeros, right? So 1365 less than this one is false, right? So you have to take 1365 less than 1 followed by 4 zeros, or 10 to the power 4. Then only this condition is going to be satisfied. Okay, then what you will do, if I divide each and every term by 10,000. So whether you can consider a beneficial attribute or non-beneficial attribute, if you divide by 10,000, okay, then you will get all the values in the range of 0 to 1, right? And other in various ways you can do, right? Various way you can solve this particular problem. But in this case, the problem is that like 1365 divided by 10,000, okay, it will come as 0.1365. And if you choose the lowest value in this particular table, I think it is 2.68, right? 2.68. So 2.68 divided by 10,000. Then you will get the value 0.000. Okay. Again another 0, then 268 if I am correct. So this value is quite small. Even if 13.1365 is also also small. But if you scan these values in between 0 to 1, so after 0.1365 up to 1, you will not get a single value. So unnecessarily will face problem while scanning these particular values. That is also one of the drawbacks of applying this decimal scaling normalizations. So people have come up with some new normalization techniques which you can apply. So in that case, you can say like in decimal scaling case, although we are facing problem with respect to scan these values, but the advantages what we are getting is that whether it is a beneficial attribute or non-beneficial attribute, we are using the same formula, right? Okay. Each and every, you need not worry about check that whether it is a beneficial attribute or non-beneficial attribute. You simply divide it by something, then all the values will be normalized to in the range of 0 to 1. That is the advantages you are going to get when you apply this weighted sum method. Okay, so come back to here. Now, as I told you, all the values are normalized. You can say the normalized to 0 to 1. So you can see here, it is showing clearly here. So performance measure values are also scaled in the range of 0 to 1. And these weight values are also normalized in the range of 0 to 1. Now we'll go for the weighted sum formula, right? What we are doing in weighted sum formula, in order to calculate the weight of this particular alternative, that is the weighted sum of this alternative. So I'm writing here, if I want to calculate the weighted sum of alternative 1. So what it will be? It will be 0.5 multiplied by 0.098. So I am multiplying the weight value with the performance value plus 0.167 multiplied by 0.308 plus 0.25 multiplied by 0.957 plus 0.083 multiplied by 0.439. So each and every performance value is multiplied with their corresponding weight value, right? After that, we sum all these values. So we got the value. If you calculate this one, can anybody calculate and tell me what is the value we are getting here? Just that we can cross check. Anyhow, I'll share the result with you. So if I do 0.5 multiplied by, you can type in your calculator also. 0.5 multiplied by 0.098 plus 0.167 multiplied by 0.308 plus 0.25 multiplied by 0.957 plus 0.083 multiplied by 0.439. So I am getting the value as 0.376123. Anybody, any answer other than this? Are you getting the same value? Can you please cross check and tell? Can anybody cross check once whether you are getting the same value or not by doing the multiplication for alternative 1? Okay, let me check the result otherwise. Yeah, here you can see the result we are getting, that is 0.376. So I have taken up to 6 decimal place. That's why I'm getting 1, 2, 3 extra. Similarly, if you go for alternative 2, what you will do? 0.5, you can take 0.5 multiplied by 0.123, right? Plus 0.167 multiplied by 0.067, sorry, 067. Okay, then plus 0.25 multiplied by 1 plus 0.083 multiplied by 0.425. Okay, so if you do so, 0.5 multiplied by 0.123, 0.167 multiplied by 0.067, 0.25 into 1, and 0.083 into 0.425. Let me see the result. Okay, first you calculate this one, then we'll see the result. Point 0.5 multiplied by 0.123 plus 0.167 multiplied by 0.067 plus 0.25 multiplied by 1. Okay, then 0.083 multiplied by 0.425. So I think you will get the value is 0.7964. So let us check the result. Yes, we are getting 358. If you take 3 decimal place, you can write it is equivalent to 0.358. Okay, so in this way, what you can do, you can take the weight value of alternative 3, weight value of alternative 4, 5, 6, and 7 respectively. So once you have calculated this weighted sum, right? These are the weighted sum values, right? You got. So you check which value is better. How to know? Highest value is better, right? Weight value means weight is more, then the result is better, right? So if you see here, these are the 7 alternatives values. So if you look into this, you will find the third alternative. Okay, this is your alternative. The third alternative is ranked as 1. So our MCDM problem, our objective is to choose one alternative out of 7 alternatives. Okay, you are given me 7 alternatives, but finally you have to choose only one alternative. And also you have to see the alternative rank. So, and order these alternatives based on the rank. Best alternative we found, that is alternative number 3. But we have to rank all the 7 alternatives, right? And arrange them in a particular order, right? 1, 2, 3, 4, 5 up to 7. Then if you see the second one, I think alternative 0. Which one is better? Can anybody guess? Which one is second position? Yeah, this one is second position. Fifth alternative is ranked 2. Similarly, you can see this is the sixth alternative. Sixth alternative, which is ranked 3. Right? Like that, you can assign one rank to each and every alternative. Okay. So see here. Yeah, exactly what we have discussed now. You can see this one is your first alternative. This one is your second, third, then fourth, and fifth alternative, sixth alternative, and seventh alternative, right? So these are the ordering based upon their weighted sum value, right? So in this way, the weighted sum methods actually works, right? So what we did, we have normalized the performance measure value in our first step. Second value, we have normalized the weight values. These all are normalization steps. Simply you have to normalize, right? By choosing the maximum value or minimum value in the case of beneficial and non-beneficial attribute case. After that, what you have to do, you have to multiply weight with the performance value. weight value is multiplied with the performance value. As you have multiple alternatives and you have to find their sum, right? That is called as a weighted sum. Okay. Weight value also you can see here that the first attribute is given as 0.5. That means it is more important to you. Third attribute is given as 0.25. So it is more important next to TI. Similarly, this is third, this is fourth. Like that, you can also say that these are the importance of different attributes in your particular problem. Like real life also, whenever there are number of attributes are there, some attributes you may be more important to you and one attribute may be less important to you. Okay, in that manner your weighted sum method actually works. So this is the first completion of the first method. Okay, if you have any question you can ask. Anyone having any question in the first method?
No, sir, it is clear.
Yeah, okay. Thank you, Samin sir. So we'll proceed towards the next method, that is called as your weighted product method. Okay, so the method is also very similar to the first method. You have to do the performance measure normalization. You have to do weight normalization. But instead of taking this weight multiplied by the performance value, what you will do, you have to take performance value to the power performance value to the power weight, right? Sometimes we are writing, right, 2 to the power 3. So it is same as 2 into 2 into 3. That's why it is called as a product based method. But actually we are doing performance value to the power weight, right? So once you get this value, suppose I want to write here only. So for the first alternative, if I want to go for weighted product method, WPM. So what I'll do for the first alternative 0.098 to the power 0.5 plus 0.308 to the power 0.167 plus 0.957 to the power 0.25 plus 0.439 to the power 0.083. Right? So if you calculate this one, you will get the value as 3.0575. I have already calculated. You can cross check this one also. Okay. So like that, you will get the values for alternative 2. Okay, I am doing one more. This is for alternative 1. Then I'll go for alternative 2. Alternative 2. So it is nothing but 0.123 to the power 0.5. I'm taking this one to the power this one. Then 0.067 to the power 0.167 plus 1 to the power 0.25 plus 0.425 to the power 0.083. Okay, if you calculate this one, you will get the value as 2.9361. Okay, so let us go to see this result. Yeah, so what we did in WPM method, we have done weighted product instead of weighted sum, which I already shown you with alternative 1 and alternative 2. We got these values. Similarly, calculate for alternative 3, alternative 4, and so on up to alternative 7. Then out of these 7 values, you have to find the maximum value. This is nothing but you can also say, instead of saying weighted product, weighted sum, you can say combined weight, right? If you see some other methods, we use that as a combined weight. So if you see the highest value among these 7 values, I think the highest value is 3.2386 if I'm correct. So this is having rank 1. That means alternative 5 is having rank 1. Okay, next to it you have, I think, another 3.2 values are there, but 3.11 is the bigger value in comparison to the next one. Okay, so I can take this one as the second best alternative or rank 2. Similarly, this is the third best alternative or rank 3. Like that, I can rank them I can rank these 7 alternatives in a particular order. So this method is very simple, right? This WPM and WSM, these methods are quite old also. I can say these methods are not recent methods. These are very, very old methods, but still you should know that how actually they works in various applications, right? They have also application in various domains like civil engineering, mechanical engineering also. People have applied this WSM and WPM methods. Like I told you, AHP, ANP, these methods are the recent methods, and mostly these methods are used, but still you can try with these methods because these methods are very, very simple. And sometimes simple methods also you can get better result rather than the complex method, right? Okay, so if it is clear to you, I'll proceed to the third algorithm. The third algorithm, yes, this is your rank 1, this is your rank 2, 3, which we have already discussed. So I'm skipping this particular slide. Okay, the next method is called as a Promethi, that is called as a preference ranking organization method for enrichment of evaluation, right? It's a very interesting method, right? But this method you need more calculation in comparison to WSM and WPM method. So you can say it is little bit complex in comparison to the previous two methods. That's why you can see in this table, instead of taking 7 different alternatives, I have considered only 4 different alternatives. Okay, anyhow, if you go for implementation, you can go for as many number of alternatives possible, right? You can go for 100 alternatives. In fact, if you go for real life data sets, you may find huge alternatives, huge attributes also, right? But I will show you a simple demonstration with 4 alternatives so that easily you can understand how actually the Promethi algorithm works. Okay, the first step is the Promethi method is nothing but normalize of weight. So you know the weight of toughness index, yield strength, density, and thermal. It is 6231 respectively. If you sum these two values, you will get 12. So if you want to normalize, you can say 6 by 12, 2 by 12, 3 by 12, and 1 by 12. Right? That will give you the normalized weight value, right? Which we have already done. No need to think about it. Okay, so you can see here, yeah, we are getting 0.5, 0.167, 0.25, and 0.083. If I sum these values, I will get 1, right? So if the value is given in the range of 0 to 1, first you have the still also you need normalization in 4 different attributes. If the values are given in the range of 0 to 1, there some may not be equal to 1. So you need normalization to make it in the range of 0 to 1. Like in this case, you are given integer values. So you have done sum of the values and you have divided in order to make it 0 to 1. Okay. For example, I'll take 0 0.1, 0 0.2, 0 0.3, and 0 0.2. So if you sum, the sum value is 0 0.8. So in this case also normalization is required, right? Not necessarily if the value is 0 to 1, you can skip normalization. The weight normalization meaning that the sum of the values is equal to 1. Why we are doing this one? So that one attribute weight should not be dependent or should not be dominant another weight value, right? If I take a very large value, right, then it may dominate also, right? So in order to avoid that, the value is scaled into in the range of 0 to 1. Okay, so we are given with 4 different alternatives and their performance measure values. So let us see how Promethi methods applied this ranking organization. We say this is a ranking organization method. How actually we do such type of ranking. So what we are doing here in Promethi method, each alternative is compared with other alternative with respect to the attribute. Like here you can see we have considered 4 different attributes. Choose one attribute and compare the alternatives with each other using that attribute. So we have 4 alternatives. We have 4 criteria also, right? So it says that to choose a particular attribute. Attribute means your criteria. criteria is first one is TI, second one is YS, third one is D, fourth one is thermal. Take one attribute, okay, compare the alternatives. Take the second one, compare the alternatives. Take the third one, compare the alternatives. Take the fourth one, compare the alternatives. Then you will combine these four. Okay, so let us see how this comparison actually takes place. So suppose I want to take attribute number one, that is TI. So for TI, the performance value for alternative 1 is 75.5. Alternative 2 is 95. Alternative 3 is 770. Alternative 4 is 187. And you know, for toughness index, higher value is better. Okay. Here also, while you are applying the comparison, you have to see that whether it is a beneficial attribute or it is a non-beneficial attribute. So for example, I am comparing A1 with A1. This is the comparison, right? If you compare four alternatives with each other, then that can be represented in the form of a square matrix, right? But alternative 1 to alternative 1 comparison is not possible. Alternative 2 to alternative 2 is also not possible. A3 to A3 is not possible. A4 to A4 is not possible, right? So what we are doing actually here, you can see when you compare alternative 1 with alternative 2, what is the value of alternative 1? That is 75.5. What is the value of alternative 2? That is 95. Which value is better? So you can say 95 is better because it is a beneficial attribute. If it is a non-beneficial attribute, you will say 75 is better. So we can say A1 is inferior to A2. That's why we put the value as 0. Okay. We are comparing A1 with A2. A1 value is 75.5. A2 value is 95. In fact, A1 is less than equal to A2 in this case. That indicates that A1 is inferior to A2. That's why the value is 0 in the matrix. Okay. Otherwise, you will put the value as 1. Okay. Similarly, when you compare A1 with A3, A1 value is 75.5, A3 value is 770. Again, you are finding 75.5 less than 770. So the value is here 0. Okay. Coming to A1, A4, A1 value is again 70.5, but A4 value is 187. Again the same case. That's why value is 0. So let us compare now A2 with A1. Okay, comparison of A1 to A2, A2 to A1, both are different. Okay, obviously, if A1, A2 comparison you got 0, that means A2, A1 comparison you will get 1. See how it will get. A2 is 95, A1 is 75.5. So if you compare, 95 is greater than 75.5. As it is better, then we are assigning here it is 1. Okay. Then A to A2 comparison is not possible. Then A to A3 comparison we will see. A2 is your 95, A3 is 770. But in this case, 95 is less than 770. It is not better. So I am putting 0 in the matrix. Take A2 to A4. A2 is 95, A4 is 187. So 95 is less than 187. Okay, 95 is less than 187. Again, you will get 0 because 95 is not better. Okay. Similarly, go for A3 comparison with A1. A3 is 770. A1 is 75.5. So 770 is greater than 75.5. So I am writing here 1 because this value is better. When you compare 770 with the second value, that is A2, which is equal to 95, again 770 is better. So I am writing 1. Okay. Similarly, when you compare A3 with A4, okay, A3 is 770, A4 is 187. So you can say It is 1 only because 770 is the highest value. So in its row, you will get all values are 1. Like that, you have to fill this particular matrix. Okay, but you have to be ensure that this is beneficial one, right? Non-beneficial case, you may get a different result. Okay, so in order to show the non-beneficial one, because you know the second attribute, that is ys, yield strength, is also a beneficial attribute. So I am not discussing this one. The similar process you can follow. I'll take the case for D, which is a non-beneficial attribute. So if I go for non-beneficial attribute, the objective is to minimize, right here. Minimize means smaller value is better. So when I compare A1 with A2, A1 is 2.8, A2 is 2.68. 2.8 is greater than 2.68. If it is beneficial, then you write 1. But here it is a non-beneficial one. That's why we put 0. Okay. So here A1 is inferior to A2. The previous case, although the value is less than, so it is inferior, right? That's why we writing like this. Then if I take A1, A3, A1 value is 2.8, A3 value is 7.9. Now you see 2.1 is less than 7.9. As it is a non-beneficial attribute, you have to write 1. Beneficial case, you put 0. Similarly, if you compare A1 with A4, it is 2.8 less than 7.9. What I can say? I can say this value is also 1. Okay. So you have to treat beneficial attribute, non-beneficial attribute differently. Okay. Proceed further. If you compare A2 with A1, so as you know, A1 to A2 is 0. No need to calculate. You put 1. You have calculated A1 to A3 is 1. So A3 to A1 is 0. You have calculated A1 to A4 is 1. So you put 0 here. So the only thing you calculate which you have not calculated, right? So I will calculate A to A3. So A2 is 2.68. A3 is 7.9. So 2 point is less than 7.9. That's why it is 1. Similarly, A2 to A4. A2 is 2.68. A4 is also same value, 7.9. So the value is 1. But you can see the value of A3 and A4 both are same. So I put, there is no comparison between A3 to A3, A4 to A4, or A3 to A4, or A4 to A3. For these values, you will get hyphen, right? Because they are not compared, because the same value you are dealing with, right? Like that, you have to calculate for all the 4 attributes or criteria. And I'm writing these 4 into a single slide. This I have calculated. I told you to do this thing in the similar fashion. This I have calculated. You can follow the same thing to calculate for the criteria thermal. Ti is calculated. Ti is your toughness index. D is your density, calculated. Yield strength follows the same structure as toughness index, and thermal consider same way as the density. So once you are ready with these 4 metrics, you also ready with the normalization of the weight values. Normalization of weight values are 0.5, 0.167, 0.25, 0.083 respectively. So now what you have to, we have to combine these 4 metrics into a single matrix. So we'll go to the first element of each and every matrix. What do we have in the first element? First element we have hyphen. So in our final matrix also it is hyphen. Let's say in the final matrix is P. So the first element is represented as P11. So it is equal to the hyphen. Okay. Now if you go for P12, P12 means I am taking this one, this one, this one, and this one. So how to write this one? In order to calculate P12, okay, you have to multiply this 0 with the weight value. 0 multiplied by anything is 0. 1 multiplied by this means you will get 0.167. 0 multiplied by anything is 0. 1 multiplied by this thing is your 0.083. So we got the value is 0.25. Now go for P13. If I go for P13, I have to choose these values, right? So 0 multiplied by 0.5, it is 0. 0 multiplied by this one is 0. 1 multiplied by this one is 0.25. And 0 multiplied this one is 0. So I am getting the value is again 0.25. Right? Coming to P14, if I solve P14, I have to take this particular value, this value, this value, and this value with their corresponding weight. 0 multiplied by 0.5, 0. 0 multiplied by 0.167, 0. 1 multiplied by this one, 0.25. 0 multiplied with this one, 0. So you get 0.25. Okay. So like that, if you do for P21, P22, P23, P24, P31, P32, P33, P34, P41, P42, P43, and P44. Okay, if you do so, you will get this particular matrix. Right? So what we did till now, again I am repeating. First we have normalized the weight. Right? Then with respect to each and every criteria, you have compared alternative AI2 with the alternative AJ. If it is a beneficial criteria, you have to see if the value is bigger, then you will write 1. If the value is not better, you will put 0. If it is a non-beneficial criteria, you have to do the reverse thing. Lower value is better, right? After that, once you get 4 different metrics, okay, what you have to do, you have to multiply the matrix value with their weight value and sum their corresponding values in each and every matrix. So you will get this matrix, that is P. Once you get P matrix, you have to calculate. Third step is your P matrix. Fourth step, you have to calculate row sum of P matrix and column sum of P matrix. Like if I calculate the row sum, it is 0.25, 0.25, 0.25, it is 0.75. Okay. Again here, if you do 0.75, 0.25, 0.25, I am getting 1.25. 0.75, 0.75, and 0.667, you will get 2.167. 0.75, 0.75, and 0.083, you are getting 1.583. That is providing you the row sum. Similarly, you calculate the column sum. Column sum, you get 0.75, 0.75, 0.75, you got 2.25. 0.25, 75, and 75, you get 1.75. Like that, you calculate the column sum. So your row sum represents your leaving flow, okay, in a particular system. This is representing your leaving flow. Okay, column sum indicates it is entering flow. So you have to calculate row sum minus the column sum. Okay, that means what you have to calculate here, row sum is 0.75 minus column sum is 2.25. Similarly, you can calculate 1.25 minus 1.75. Similarly, you can calculate 2.167 minus 0.583. The last one, 1.583 with 1.167. 1.583 minus 1.167. So if you calculate, you will get these values. Okay, this is nothing but the difference between the leaving flow and entering flow. Okay, once row sum and column sum is calculated, you have to find their difference, and the difference value, you have to find the highest value that is given as the first way. or that is considered as your best alternative. So in this case, as we choose the maximum value, that is A3, because after the process of normalization, maximize and minimize are reduced to maximum. Maximize is as it is maximize, but minimize problem we have converted to a maximization problem, right? Genetic algorithm also we have studied, right? So that's why we are choosing the maximum value. So A3 is said to be the best alternative, followed by A4, followed by you can say A2, followed by A1. So these are the different alternatives and they are ranked as per the Prometheus algorithm. Any question related to Prometheus?
Hello.
Yeah, Samin sir, please.
You are actually showing this thing to us. But is it possible to calculate all this thing automatically through Excel or like that?
Yeah, you can do using Excel also. You can write the code in any programming language, MATLAB,
Okay.
C, C++, Python, okay? Or you can do the same thing in Microsoft Excel also.
Okay, great. Okay, sir. After your lecture, actually, I have some question on this regard.
Yeah.
Thank you very much, sir.
Yeah, okay. Okay, so here one observation you can make where we have improved in our algorithm. Like if you see this particular matrix, right? You concentrate on this toughness index. In toughness index matrix, either the value is considered as 0 or the value is considered as 1 while comparing one alternative with another alternative. Right? Which one is not a paired one, right? Why it is not paired one? If 700 is greater than 1, you will write 1. If 70,000 is greater than 1, you also write 1. Right? On the other hand, if you go for the reverse one, right? Like if I say this is 1 less than 700 or 1 less than 70,000, okay, in that case, you put the value as 0. Right? So this type of difference you are not finding in this particular matrix because we represent everything in the either in the 0 or in the 1. So what we did, we considered that one particular value, how much it is inferior, how much it is not inferior, that you can calculate. So we have observed that if you go that one, Prometheus is providing a better ranking in comparison to this one. Right? You can go to my Google Scholar and find that particular paper. If you need, I will also share that paper. So in which we have considered the values in the range of 0 to 1 rather than it is only 0 or 1. In that way, the Prometheus method can be extended, right? Or you can focus on other parts where there is a scope of improvement. You can improve these methods. Okay. Now let us come to the next method that is called as Vickers method. I told you this is a Serbian term. This method is also known as a compromise solution or compromise ranking method. Right? More or less, you can see the steps are same as the WSM and WPM method. The WSM method we have seen, we have to do performance measure normalization. We have to do weight normalization. So let us see what we are doing here. Again, in this case also we consider the first two attribute, that is Ti and Ys, they are beneficial attribute, and D and T I have considered as a non-beneficial attribute. Obviously, our objective is to maximize the beneficial attribute and minimize the non-beneficial attribute. And these are the things you already know. There are 4 different components we have seen in MCDM. One is alternative. So 7 alternatives we have considered here. And we have attributes. So we have 4 different attributes. We have weight. So our weight value is, there are 4 different weight, right? 4 different criteria means there are 4 different weight. They are 6, 2, 3, 1 respectively. And the performance measure values are you can see in the form of table, right? So like WSM or WPM method, we did the normalization by taking the same formula, x is equal to x divided by x max, or x is equal to x min divided by x. Okay, one is beneficial attribute, another is called as a non-beneficial attribute. Okay, we have done this thing based on that. Okay, now once your performance measure values are normalized like this, you can also go for weight normalization, which is not given here, but later point of time we have done the weight normalization. So up to this, the WSM and WPM method is same as the weaker method, right? Performance measure you have to normalize, you have to also normalize the weight value, right? Now what Weaker actually does here, it is finding the difference D in each and every column by considering the maximum and minimum values. Like maximum values, if you see in this particular column, okay, it is equal to your 1. You know, in each and every column you will find maximum value is always 1, and the minimum value is your 0.098. So like any optimization algorithm, we take the best solution, we take the worst solution, so that we will know what is the gap. If the gap is very less, that means all the populations are more or less providing the same solution. But if the gap is more, then we can consider that best solution is very worst solution is very away from the best solution. You need more iteration so that they need to be closer to each other. Okay, so we found the D here is maximum minus minimum. So if you do 1 minus 0.098, so you will get the value is 0.902. Similarly, you take the second column, you will see the maximum value is equal to 1 and minimum value is 0.067. So if you find the difference, you will get the difference is 0.93 and 3, right? But whether it is a beneficial attribute, non-beneficial attribute, you have to find the difference between the maximum minus minimum, right? Because minimum is now converted to the maximum. Non-beneficial attributes are now, by dividing them in this manner, that is x mean divided by x, they will convert it to the maximum one. That's why you need not worry, right, while calculating the difference. Okay, so we have calculated the difference. After finding the difference, what you will do? Just like you have seen Jaya algorithm, you have seen Rao algorithm, different variants of Rao algorithm. We'll take only one alternative here, right? Here you can see the weight is normalized. I told you, na, weight is also you have to normalize. The way you have normalized in WSM method, the way you have normalized in WPM method. Okay, so now if you come to here, so what we are doing, we are taking the first alternative, okay, with the maximum value and minimum value, or you can say the D. Then we will do the second alternative with D, third alternative with D. By using that, we will calculate. Like here, the first alternative, we know it is, these are the values, and this is the difference value we found among all the alternatives. This value, this difference is calculated based upon the maximum and minimum value. So maximum minimum value means you have considered all the alternatives. So you will calculate E is equal to summation over W max minus X divided by max minus min. What is W? Generally, we consider the W is nothing but the weight, normalized weight value. So you have taken 0.5, 0.167, 0.25, 0.083. That means this is for your criteria 1, first criteria. This is for your criteria 2. This one is for criteria 3, and last one is for criteria 4. Okay. So what we did here, 1 minus 0.098. So this one, that is 0.092, what we are doing here, maximum minus X. Similarly here also we did 1 minus 0.308. Okay. So what we are doing, sorry, this is not the calculation, just a minute, I told you wrongly. So what we are actually doing, we are taking the maximum value in each and every case is 1, and we subtract it with the corresponding value. The corresponding value is 0.098, 0.308 here, 0.957 here, and 0.439. Okay, that is max minus x means this max is nothing but 1, x is nothing but your alternative alternative one's performance value, right? But in the denominator part, you will put this d value. D values are 0.902, 0.933, 0.686, 0.575, and 0.575. Then you will get the value of E1. So E1 value you got here is 0.7205, right? Similarly, if I take second alternative 2 with D, okay, so what you will get, again the weight values remain same, right? These weight values I put here, okay. D value remains same. These are the D values is there in the denominator part, you can check, okay. Maximum value, you know, in each and every case it is 1 only, and the performance value only you have to put here. Performance values means these values. So you can see first case we put 0.123, 0.067, then 1, then 0.425. So if you calculate this one, you are getting 0.7361. Similarly, calculate for the third alternative. Only you will see these values are going to be changed. Right, rest value is same because weight is same for all. Maximum minus minimum is same for all. Right, only this x value is different. Okay, do it for fourth alternative, fifth alternative, sixth alternative, seventh alternative. Okay, so once you calculated for all alternatives, put in a column that is called as E. Okay, so you can see here in the first case, if you remember what we have, first case we have the value. If you go for alternative 1, I am writing alternative 1, you got 0.5 plus 0.1239 plus 0.0157 plus 0.081. Sum you get as 0.7205 that we put here. Okay. Then what you will do, like that you will calculate for each and every alternative, and the values are here only, right? Now we calculate P1, okay, and before P we have a column that is called as F. F says that out of these 4 alternatives, okay, sorry, out of these 4 criteria, this is for criteria 1, this is for criteria 2, this is criteria 3, and this is criteria 4. Out of these 4 criteria, which criteria is having higher value? So we got the highest value is 0.5. Similarly, if you go for the second one, this is the criteria value for C1, C2, C3, C4. Combined we are getting this one, that's fine. But which term is contributing more? So that we will know the importance of the criteria. So we calculate that as 0.4861. Right, like that you can get the values in this particular column. Okay, now in order to calculate the p value, okay, p1 if you calculate for the first alternative, you can calculate using this particular formula. What is that? V is nothing but a weight value that you have to determine. So in order to be a equilibrium or equal value, we consider B is also 0.5. So 1 minus B will come as 0.5. So both term we are treating equally. And first term is related to this particular column E. And second term is related to the column F. So what we are doing here, in the first term, E minus E mean. E means 0.7205 minus E minimum. E minimum we got a 0.3050. E minimum means out of these which one is minimum? The minimum is this one. out of these, which one is maximum? This one. So every time we want to find this minimum and maximum, right? So the main idea is to, we want to see that how much we are deviating, right? Based upon that, we are finding the rank, right? So similarly here in the second term, you are finding f minus f minimum divided by f max minus f minimum. So f max is 0.50 and f minimum is 0.2409. Okay. So you need E column, F column, determine E max, F max, guess at V value, right? Generally we take V value as 0.5. Otherwise, you will say E and F terms are having different weight value. If I take V value as 0.7, then 1.1 minus V becomes 0.3. So in that case, what will happen? So one term may dominate another term, right? In this way, you calculate this p value. Okay. After calculating the p value, okay, you will see the lowest value. Here we consider the lowest value as for this calculation. The lowest value is considered as the best rank. So if you check in this value, the lowest value we are getting in the case of alternative 3. So alternative 3 is ranked 1. Similarly, the next lowest value is alternative 2, right? So that is considered as your rank 2. So each and every algorithm, you have based upon the calculation, they suggested whether to choose the minimum value or to choose the maximum value. Okay. So based upon that, you have to determine the rank and choose the best alternative. So more or less, we are looking here that the third alternative is the best alternative. Okay. Okay, proceed further. Another algorithm that is called as a TOPSIS, okay, which is also a very popular algorithm, which stands for a technique for order preference by similarity to the ideal solution, right? So what we are doing here, we have taken uh, same 7 different alternatives, 4 different criteria. Criteria weights are given to you, so you have to normalize this weight. Every case you are normalizing, so that is not new, okay. And you are also normalizing the the performance measure values, right? That is also not new. But here what we are want to find, we want to find the denominator D. Okay, denominator D can be found by taking the square of each and every performance value under a particular criteria or attribute. Like here you have, under this criteria you have 7 values for 7 different alternatives. So find their square. If you find their square, we got value 57009025 and so on. Okay. So if I sum this Ti square, sum of the, you can say sum of each criteria's square. Okay. Where I is equal to 1 to 4. 4 criteria are there. You have to find for criteria 1 square, criteria 2 square, 3 square, 4 square, right? So we got this one. If I take root over of that, that will give me D. So D is equal to root over of sum of I is equal to 1 to number of criteria, that is 4, and Ci square. So I got the value is 897.9339. Okay. Similarly, what you have to do, you have to calculate for second one. This is for Ti. Again, you have to find for Ys also. Ys is also, you have to make the squares, sum the square, okay, sum all the square and take the root over. Then you will get the denominator D is equal to 2350.3257. Do this for the another criteria, that is the D, okay, and another one that is T, okay, D, and another one is T. So you will get the denominator value as 17.4541. In another case, you are getting 4.45.3427. Right? Now, after doing this one, after finding the denominator value, So the way of normalization is changed here. The reason of finding this denominator is that earlier you are finding the maximum value, right? Or non-beneficial criteria case, you are finding the minimum value. Okay. After finding maximum value, we are dividing with each and every performance measure value. And if it is a non-beneficial criteria, then numerator part you are taking the minimum value. But what we did here, we after finding this denominator value, the denominator is divided. Okay, from each and divided by the denominator is divided from each and every performance measure. The performance measure value is 75.5 and denominator is 897. So we got the value as 0.0841. Okay. Similarly, here denominator value is different. So I will do 420 divided by 2350. Here denominator is again different. So I am taking differently. Okay. So after finding denominator, what happened? More or less, now weight is normalized. Weight is normalized as per the previous policy only. We have to find the sum of the weight and divide from each and every weight value, right? Then we got these values. So these values we found from the denominator. Earlier we calculated based on either x max by x, or we did by x mean by, sorry, just a minute. Okay, we did it by x divided by x max, okay, for beneficial attribute, and x mean divided by x for non-beneficial attribute, right? But now we have changed that one, right? So what we will do next one? Now we will apply the weighted sum method. Can anybody tell what is weighted sum method? What we are doing in the weighted sum method? If these values are given to you, if I ask you to apply the weighted sum method, how will you apply weighted sum method? Any answer? Weighted sum method. You are multiplying the weight with the corresponding performance values, right? Weight with the corresponding performance values. So if you calculate here, it is nothing but 0.5 multiplied by 0.0841, then 0.1787 multiplied by 0.167, 0.1604 multiplied by 0.25, 0.4720 multiplied by 0.083. So that will give you, if you multiply this, you will get these values. Okay. So once you are ready with these value, you have to calculate two other factor. One is called as SP, another is called as SM. Okay, just like sum of product and some weighted sum and weighted product. Here we are calculating two other factor. One is called as SP, another is SM. So how to calculate SP? So in order to calculate SP, you have to take 0.0421, that is your performance measure value, minus 0.4288, which is the maximum value, right? Similarly, 0.0298 minus 0.097. 097 is the maximum value. Okay. But minimum case, you have to take 0.0401, which will, and the minimum value, that is 0.0384. Similarly, it is also a non-beneficial attribute, so I have to take the minimum one. Okay. So you have to find the difference, make their square and sum it. Then find the root over. You will get the value of SP. Similarly, if you go for the value of SM, okay, in SM what you are doing? There you did with the maximum value. Now we did with the minimum value. So minimum value is this one, minimum value is this one. Here the minimum value is nothing but your maximum value, because it is a non-beneficial attribute. Okay, so here you can see 0.0405 is a non-beneficial attribute. So I got SM is equal to 0.0854. Like that you find for all the alternatives, SP value and SM value. Once you get this SP and SM value, you have to calculate P P value is nothing but Sm divided by Sm plus Sp. Okay, and highest P value is considered as the best alternative. Okay, like here you can see this is the SP value, this is the SM value. If I put SM value, that is nothing but 0.0854 divided by 0.0854 plus 0.3931. So I am getting the value as 0.1785. Okay, and the highest one among these values is which one? 0.8395. So it is considered as the best alternative. Okay. Now we'll go for the last method, that is called as a graph theory matrix approach, that is called as GTMA. Okay. So this GTMA is a logical and systematical approach which originated from combinatorial mathematics. All of us aware of a matrix, or all of us aware of the determinant, right? The same concept is applied here. So GTMA helps to analyze and understand the system as a whole by identifying the system and subsystem up to the component level. Many MCDM methods are there. They are giving decision based upon the system level without looking into the subsystem level. But when you go for GTMA case, you will not consider subsystem level, but also you will consider subsystem level and consider that as a whole one, complete system. GTMA helps in selecting the most suitable choice from among a large of alternative for a given problem. In fact, all the MCDM methods is selecting the most suitable choice from a set of alternatives. So matrices provide a simple and very elegant means of representing the graph, as it gives one-to-one representation. If a matrix, like we are aware of as a computer science faculty or computer science researcher, so we are aware of adjacency matrix, right? So there also you can convert that matrix into graph. Similarly, here also you can convert it into graphs by representing each and every alternative as one node, and you can say the relationship between two nodes can be represented by writing a link. Okay, so see here in GTMA method, we have taken 7 different alternatives, 4 different weight value. Then again, beneficial criteria are the first 2 criteria, non-beneficial criteria is the next 2 criteria. Our objective is to maximize Ti and Ys, the first 2 attribute. And our objective is to minimize the non-beneficial attribute, that is D and T. And same thing, whatever we have discussed, there are 7 different alternatives, 4 different attributes. Their weight values are 6, 2, 3, 1 respectively, and the performance measure values are also given. And normalization process is same as the WSM method and WPM method. So you will get these values. Okay. So once you get these values, the process of GTMA is different from WSM and WPM. Up to this, it is same. So what we are doing here, in order to generate the weight value, normalized weight value, earlier what we did, we have sum all the weight value, which is 12. Then we have calculated 6 divided by 12, 2 divided by 12, 3 divided by 12, and 1 divided by 12. Okay, but now you need not do this one. There is different weight calculation. So this weight is calculated by comparing one criteria with another criteria. Previously, you are comparing one alternative with another alternative. Now, this Ti, Ys, D, and T, these are called as your criteria. So we are comparing one criteria with another criteria, right? So while you are comparing, you are representing in the form of a matrix, which we call as a relative importance matrix. Like when you compare Ti with Ys, you will get the weight value can be calculated as Ti divided by Ty plus Ys. So Ti is 6 divided by 6 plus 2. So I'm getting the value as 0.75. Similarly, when you compare Ti with D, okay, so it is Ti divided by Ti plus D. Okay, so you will get Ti value is 6, Ti value is 6, D value is 3. So like that, when you compare one criteria with another criteria, you will get a weight value. Then what we are going to do, we have already normalized the performance values of each and every alternative. And we are also ready with the normalized weight value by comparing two different criteria or attribute, which we call as a relative importance matrix. Now we'll take these normalized performance measure values, we'll put in this diagonal. Okay, so if you do so, it looks like this. You can see I have taken the performance values of alternative 1 and put in the matrix, right? If you put in the matrix, then you can solve this matrix like this, the way you are solving a determinant. But you can see in determinant case you have plus and minus, but in this case we consider all the things as plus. So I'll take this 0.098, I'll off this row as well as column, I'll take the rest part here. Okay, similarly when you go for 0.75, that is the second one, so you have to off this column as well as off this row and take the rest part here. Similarly, if you go for D, you have to take 0.667, then you have to off this column, this row, then take the rest part here. Last one, when you take 0.857 of this column, of this row, take this one. And apply, you know how to solve the matrix determinant, right? So if you solve, you are getting the value as 0.8182. Similarly, you put the performance values of alternative 2 here and solve it, that will give you the performance value, the value for alternative 2. Okay, that you will get here 0.7391. Like that, if you solve A3 value, you are getting as 1.6257, A4 value you are getting as 1.0149, and so on. Out of these value, the highest value you got here is 1.6257. So that is considered as one of the best alternative, right? So in this way, if a MCDM problem is given to you, you can solve the problem by applying the MCDM methods. But make sure that you have to select one of the alternative out of a set of alternative. In that case, MCDM or MADM methods will be helpful to you. You can try multiple methods and you can see the alternatives, right? Which alternative it is performing better. Based upon that, you make a judgment. So this is all from my side. If you want, you can refer the material by Professor Saroj Kumar Patil. Yeah, thank you everyone. If you have any question, you can ask.